Welcome, everybody, to the tutorial on the fairness in AI systems. And while we are waiting for maybe a couple more people to trickle in, please go to this, check out our little icebreaker poll. So if you go to this website and enter the code, you'll have a little question that will allow us to kind of figure out a little bit about how much you know, what do you think when you hear fairness in the context of machine learning. And as a little reminder, we have set up a Google Colab that you can use to follow our tutorial along. So this work this tutorial is a collaboration among a team of people. All of us are not actually working for the same company. All of us are contributors to the Fairlearn open source project, which is completely community driven, but we have various affiliations. My name is Miro Dudik. I am a researcher at Microsoft Research, and there's a couple of other folks from Microsoft Research. Then we have people from universities like University of Washington and Technical University of Eindhoven, and as well as from other companies, some of them in Europe, like Zalando, as well as in the United States, like Data IQ. A little bit of logistics. So during the tutorial, feel free to ask any questions in the chat. We have several of the team members online that will be able to answer those. Occasionally, I will also ask if anybody has any further questions, and so if there is something that merits attention of the whole crowd, we can deal with that in the presentation. But if you have questions, don't wait for asking me. Just jump into the chat, and some of our team members will come to answer. And I see people have started filling out their the poll. That's awesome. So so let me see whether we have still folks trickling in. I think it's somewhat stabilized. So let me just show you the word cloud that you've all created so far. And so we see quite a few words coming up, things like equality, equity, ethics, unbiased, bias, intersectionality, discrimination, proxies, good practice, privacy, a lot of good words. A lot of good words. I'm very curious what this will look like when we run a similar survey at the end of our tutorial. So let me then jump in back to the presentation. So as I mentioned, this is work of a large team. We are all contributors to the Fairlearn project with a variety of affiliations. I would like to acknowledge where various content that I'll be presenting comes from. So the slides that you will see in this overview have been developed by Hannah Wallach, who's on the chat actually, as well as Jen Wortman-Bon and a couple of other members of the Microsoft Ether Fairness and Inclusiveness Working Group. Then we will be using a healthcare scenario throughout our tutorial, which is heavily motivated by the work of Obermeyer et al. From 2019. And finally, our data set was developed by a team of folks from Virginia Commonwealth University and a couple of other institutions. Well, at the risk of stating the obvious, we are living in the age of AI. Machine learning is everywhere, and at least for now, it looks like it's here to stay. And in many ways, this is great. But at the same time, we're starting to see that these new opportunities brought about by AI and machine learning also raise new challenges. And in particular, these are the challenges that have received a lot of attention in the media and have really highlighted how important it is to get AI right, how to make sure that AI does not discriminate or further disadvantage people that are already disadvantaged. Some of these media stories have involved high-stakes decisions where AI systems are used to allocate opportunities or resources in ways that can have significant negative impacts on people's lives. For example, I'm sure many of you have heard about the ProPublica investigation a few years ago, which showed that Compass, which is a widely used recidivism risk assessment tool, incorrectly scored Black defendants as high risk more often than the white defendants. And simultaneously, it incorrectly scored white defendants as low risk more often than Black defendants. Now, there are some other stories that seemingly involve much more mundane AI systems. For example, researchers at Princeton found that translating he is a nurse and she is a doctor into Turkish, which is a genderless language, and then back into English yields the stereotypical, and in this case, actually also incorrect sentences. She is a nurse and he is a doctor. These stories are examples of AI systems behaving unfairly. But even though we can often spot fairness-related harms in AI systems when we see them, there is no one-size-fits-all definition of fairness that applies to all AI systems in all contexts. Moreover, fairness in AI system is a fundamentally socio-technical challenge, meaning that it cannot be purely approached from either social or from purely technical perspectives. Taken together, these factors can make it a pretty daunting landscape to navigate. But although there are few easy answers, there are a variety of strategies emerging for assessing and mitigating fairness-related harms, as well as a deepening understanding of the challenge throughout society. And that's what we'll explore in this tutorial today in the context of a scenario that we have drawn from healthcare. In this tutorial, we begin by the overview of fairness in AI systems more broadly, and then we introduce our specific healthcare scenario. We begin by exploring some of the definitional issues and some of the dataset issues before we move to showing how we can assess the fairness of a machine learning model. And finally, in the last section, we will focus on mitigating fairness-related harms in machine learning models and conclude. So this is what we will cover in this tutorial. Let me also tell you what we will not discuss. I want to highlight one really, really important aspect, which is that while fairness is related to the concepts in anti-discrimination law, in this tutorial, we will just focus on fairness and largely will not touch the legal considerations. One important aspect to note is that the fairness, which is typically based on some specific definition, is one axis, and the law is another axis. And so it is possible for the system to be fair, but something you cannot deploy because it's illegal to do so. And also vice versa, it is possible for a system to be exhibiting no legal discrimination, but at the same time exhibit a variety of fairness issues. And since we will be focusing on fairness rather than on legality, we will also try to avoid legal terminology, such as discriminate against, protected class, disparate treatment, and disparate impact. Okay? Well, if you have heard anything about fairness in AI systems, you've probably seen the word bias get thrown around left, right, and center, often as a catch-all way to describe any unfair behavior of any AI system and any possible causes of that unfair behavior. However, in this tutorial, we're going to avoid using the word bias wherever possible, and we recommend that you try to do the same. And the reason for this is that the word bias is very ambiguous and means very different things to different communities. For example, we can have social bias that tends to refer to prejudice against a person or a group. There is also statistical bias, which is systematic error in the estimation of some parameters or variables, as well as there is systemic bias that refers to inherent tendency of a process or a system to support particular outcomes. And there are many, many different kinds of bias, and very often some of the issues that we're dealing with when discussing fairness of AI systems touch on all of these and more. So instead of bias, we will focus on impacts that AI systems can have on people. This precision is going to be useful in disentangling who might be harmed by a system and in what ways, as well as suggesting different assessment and mitigation strategies. On that note, I would also like to emphasize that because there are so many different reasons why AI systems can cause fairness-related harms, it is not really possible to fully debias a system or to guarantee its fairness. Because of this, we will not be talking about words like debiasing or unbiased, which can set unrealistic expectations. Instead, we will recommend talking about assessing and mitigating fairness-related harms. In other words, we're suggesting more of an iterative process and an iterative mindset that allows us to improve and continue improving the system while being alert to possible new issues as they arise. So I've been mentioning fairness-related harms. So let me dig a little bit deeper. Broadly speaking, there are three main types of fairness-related harms that can be caused by an AI system: allocation harms, quality of service harms, and representation harms. To explain each of these three types, I'm going to run through some illustrative examples, starting with the most well-known type, which is allocation. But before I do that, I want to note that these types of harms are not mutually exclusive. It is possible for a single AI system to exhibit more than one type of harm. And in fact, many of the examples that I'll show you could have been used to illustrate one or more of the other types as well. And finally, I also want to mention that some of these harms kind of act in conjunction to create new kinds of harms, such as alienation and stigmatization. So the allocation harm, as I said before, many media stories have focused on high-stakes decisions where AI systems are used to allocate opportunities or resources in ways that can have significant negative impacts on people's lives. For example, Amazon abandoned its automated hiring system after finding that it amplified the existing gender imbalance in the tech industry by withholding employment opportunities from women. Quality of service is all about whether a system works as well for one person as it does for another, even if no opportunities or resources are extended or withheld. For example, researchers found that 3 commercial gender classifiers had higher error rates for images of women with darker skin tones than for images of men with lighter skin tones. Similar to accessibility issues, quality of service harms can raise questions about respect, dignity, and personhood. Imagine how a user might feel if a system repeatedly fails to recognize their voice, but easily recognizes those of their peers. The third type are representation harms. There are many different kinds of representation harms, including stereotyping, denigration, over and underrepresentation. The harm of denigration, which is the one that I'm illustrating here, occurs when an AI system is itself part of a process that is actively derogatory, demeaning, or offensive. For example, a few years ago, Google Photos infamously mislabeled an image of Black people as gorillas. This mislabeling is harmful not just because the system made a mistake, but because it specifically applied a label that has a long history of being purposefully used to denigrate and demean Black people. I would like to reiterate that these 3 types of harms are not mutually exclusive. A single system can exhibit more than one type of harm, as I've indicated here on this slide, and can even exhibit harms for different harms for different groups of people. Finally, fairness-related harms can have varying severities. For instance, unfairly denying someone bail is a more severe harm than labeling an image of a female doctor as a nurse. But it's also important to remember that even relatively non-severe harms can make people feel alienated or singled out, and their cumulative impact can become extremely burdensome. Are there any questions at this point?
No questions right now. Thanks. Oh, someone just asked, what is fairness?
But by fairness, I think, like in the context of this talk, Fairness, fairness per se will have a variety of different definitions. When we're talking about fairness, we're thinking about mitigating different fairness-related harms. So all of this, so we're thinking about everything through the lens of harms. So fairness will have a variety of different operationalizations, but the key focus to take away at this point is that we would like to ensure that these fairness-related harms of allocation, quality of service representation are reduced in an AI system. Okay. So I gave you examples of the fairness-related harms. And so now the question is who is affected by these fairness-related harms? Sometimes it's the people who will use or operate a system, but it can also be other stakeholders who are directly or indirectly affected by a system, either by choice or not. For example, in the case of a facial recognition system for workplace building access, the system operator is not the person whose face is being recognized, and thus not the person who is most immediately harmed if the system makes a mistake. I also want to emphasize that although media stories often focus on groups of people that are protected by anti-discrimination laws, such as groups defined in terms of race, gender, age, or disability status, there are actually many different groups of people that we want our systems to treat fairly, and it's not always easy to identify the most relevant ones, which can even be specific to the domain or use case. For example, in the case of an automated essay grading system, whether someone is a native speaker of the language may be more relevant than their age or their disability status. It's also important to remember that groups intersect and people within those intersections may be at risk of experiencing unique harms that might be obscured by considering only non-intersected groups. Returning to the gender classification example that I mentioned earlier, error rates were significantly higher for images of women with darker skin tones than for images of women overall, or for the images of people with darker skin tones overall. The researchers who conducted the study were only able to uncover these disparities by assessing system performance with respect to skin tone, and at the time they were only considering binary gender. So how do these harms arise? So was there another question?
Yeah, Joe asks, is it AI introducing the deviation or the people developing it?
It's all of the above. In fact, like like this is this is a wonderful segue to this slide. So how do these harms arise? Why do AI systems cause fairness-related harms? Well, if you look at the way that AI systems are portrayed by the media, you'd naturally assume that the only reason is biased data sets, so-called biased data sets. But in reality, the situation is more complex than that. Not to mention the fact that phrase biased datasets is often used to refer to datasets with any number of undesirable characteristics, such as reflecting stereotypes in their content, or perhaps too few data points about some group of people. So over the next few slides, I want to run through some of the different reasons with some examples so that you'll know what to look out for in your own systems. First, though, I want to explicitly emphasize that although there are many reasons why AI systems can behave unfairly, these reasons rarely include bad intentions on the part of the teams responsible for developing or deploying those systems. All right, so starting with datasets. Some AI systems behave unfairly because of societal biases that are reflected in the content of the datasets used to train them. Returning to Amazon's automated hiring system, the system withheld employment opportunities from women because the data with which it had been trained reflected the existing gender imbalance in the tech industry. Other AI systems behave unfairly not because of societal biases that are inherent to the datasets used to train them, but because of other dataset characteristics, such as too few data points about some group of people. For example, the reason why the three gender classifiers that I mentioned earlier had higher error rates for images of women with darker skin tones was because there weren't enough images of women with darker skin tones in the data sets used to train them. In some cases, the relative proportions of different groups of people in the data set may even reflect reality, but such a sampling strategy can still lead to insufficient data about groups that are smaller. As another example, some AI systems behave unfairly because of assumptions about what a particular data set captures and how this relates to the system's purpose. For example, a crime prediction system trained on an arrest data set relies on the assumption that the number of arrests in a neighborhood is a good proxy for the amount of crime committed there. But this assumption fails to account for high rates of arrest without conviction or for over-policing in less affluent neighborhoods. So the resulting system may make inaccurate predictions that reflect historical policing practices rather than the occurrence of crime itself. Finally, sometimes the issues with the task definitions are more fundamental and can reflect misunderstanding about what AI can and cannot do. As an extreme example of what can go wrong here, in 2016, a paper came out by a group of researchers who proposed training a facial analysis system to predict who is going to commit a crime based on images of people's faces. This is extremely worrying for a whole host of reasons and could lead to substantial harms for people who are misclassified. I hope it goes without saying that even with good intentions, this is a questionable system purpose and not something that AI is actually capable of doing. The examples I showed you are by no means comprehensive, but I hope they've convinced you that there are many reasons why AI systems behave unfairly. Sometimes AI systems behave unfairly because of societal biases that are reflected in the data sets used to train them, or because of other data set characteristics, such as too few data points about some group of people. And sometimes it's because of assumptions or decisions made by teams, either explicitly or implicitly, throughout the AI development and deployment lifecycle, such as the choice of the label, choice of the objective, and in fact, the very choice of the task. Because there are so many reasons, and because these reasons are not mutually exclusive and tend to exacerbate one another, assessing and mitigating fairness-related harms are not things that can be treated as an afterthought. They need to be prioritized at every single stage of the AI lifecycle. Any questions?
Yeah, we have one in the queue from Niles. Are harms resulting from AI systems qualitatively different from harms from other complex systems, like other human social political systems and institutions?
I think that some of them are similar, but because the system has a technical component, they require often the combined intervention. So there is definitely place for social interventions only, as well as technical interventions only, but they will not work as well as an intervention that is aware of both components. And so definitely there's like a lot of connections with AI systems versus other complex systems, but or other systems that have impact on society. But what makes, I think, AI systems perhaps more unique is that they're socio-technical. Any follow-up?
Let's give a few seconds because I think last time we had one pop in right when you started up again. Okay, I think we're good.
Cool. So let me summarize what we've seen so far. So in this a very high level overview, I've told you about three main types of fairness related harms. The harm of allocation, which is when the system allocates resources, opportunities, or information in a way that leads to disparities in outcomes. We talked about quality of service harms, which is when the system does not work similarly well for all groups, as well as representational harms, which is the system that reinforces negative stereotypes, denigrates, over or underrepresents certain groups. Now, now in this context, like kind of cycling back to the question what it means for a system to be fair, like systems that is more fair. So again, like it's again the question of extent and this question of iteration. The system that is more fair will exhibit fewer of these fairness related harms. So perhaps like that's a that's a better answer, and we'll see how we can start go about formalizing it later. Okay. Now, groups at risk of experiencing harm are context dependent. And I mentioned the examples from that they can be just demographic groups that are even protected by law, but some of the groups, such as in speech recognition systems, might be a little bit domain specific, such as native or non-native speaker. And finally, fairness-related harms can be introduced or propagated at every stage of AI lifecycle. At the stage of task definition, data collection and pre-processing, model training, model evaluation, as well as model deployment and monitoring. And therefore, the assessment and mitigation should also take place at every stage. So with this, I'm going to switch from the PowerPoint to the notebook. So I'm not sure whether everybody has the link, but I think as I'll be running from the Jupyter. Let me but if you still don't have the link, then you can find it at tinyurl.com/ Fairlearn SciPy tutorial is the link that will take you to the README, and from here you will be able to go to the Google Colab. Okay, maybe one of the others can post it also in the chat. Okay.
Miro, I think we have as you transition, I just want to say we have I think a little bit of a follow-up question to the last one.
Oh, fantastic! Sure, let's take it.
So Bob, I think it's a follow-up, says, how is AI distinctly different from other socio-technical systems in terms of fairness-related harms?
I think my sense is that it's not distinctly different. It's just that because that folks the folks in AI basically need to be aware of the entire scholar, like of the specific parts of this social and technical systems scholarship, right? And so again, we as experts, like folks that are experts in AI, need to be making this fairness interventions and mitigations while aware of the other parts. So the way I think about it is not necessarily that they were vastly different from other socio-technical systems, but because of some of the issues that come up related to scale and obscurity, and black box and hype, we just kind of like need to be sure that we apply the lessons of the past well, and we apply them to AI systems. So the way I think about it, this is more like a special case of the socio-technical system, right? And so there will be a little bit of things that are more idiosyncratic as a result, but a lot of general techniques that apply to general socio-technical system apply here as well. So I would not necessarily argue that it's deeply different. Okay.
We have a little bit of a housekeeping question. Is it okay to share some of the material from the slides Colab notebook with my class?
Absolutely. So you can just kind of go. As I select, so here, as long as the tutorial itself is under CC BY 4.0 license, and then like as long as the tutorial itself, the slides you can share as long as you give proper credit as usual. So it's available on GitHub. Okay. The slides are available on GitHub as well. Okay. So now that we have walked through some of these questions around from this kind of high level point of view of the questions of fairness in AI systems, I would like to, and we're transitioning to working with our notebook. I would like to mention some of the tools that we'll be using and libraries throughout our notebook. So some of them are standard machine learning and data processing libraries such as scikit-learn, pandas, numpy, as well as standard plotting tools like Seaborn and Matplotlib. And we will be also using two libraries that are specifically targeted at AI fairness. So I mentioned that we are contributors to the Fairlearn project, which is an open source community-driven project. Our goal is to help data scientists improve fairness of AI systems. And besides providing a Python library for fairness assessment and improvement, where we are also trying to develop educational resources that cover organizational technical processes for unfairness mitigation. As I mentioned, I am from Microsoft Research, and the project was started in Microsoft Research. But earlier this year, we switched to a completely neutral governance structure, and so at this point, no single entity dominates the decision making, and the project since then has been fully community driven. The second library that we'll be using is a model card toolkit, which seeks to streamline and automate generation of model cards, which are machine learning documents that provide context and transparency into models development and performance. This was released by Google in 2020. So, are there any questions at this point?
None in the queue, but we might want to wait a few seconds. Okay, we're good.
Very good. So with that, let me jump into the healthcare scenario that we will be exploring throughout this tutorial. Our scenario builds on previous research that highlight. Oh, sorry. By the way, one question: can you see this well, or do I need to increase the font size? Maybe one of the speakers, if you can chime in. Okay, I see thumbs up, so I'm assuming that this is good. Okay, great. So perfect. Oh, that's cool. And I like this. So our tutorial builds on the previous research that highlighted racial disparities in how healthcare resources are allocated in the United States. Motivated by that work, we consider an automated systems for recommending patients for high-risk care management programs. These programs seek to improve the care of patients with complex health needs by providing additional resources, including greater attention from trained providers to help ensure that care is well coordinated. The key part about this, so I will not go through the rest of the quote, is that these healthcare systems rely extensively on algorithms to identify patients who will benefit the most. We're going to make one convenience restriction, and I want to raise this as a flag up front, which will kind of speak to some limitations of the conclusions that we can draw from this. So in practice, the modeling of health needs would use a large data set that covers a wide range of diagnoses. But in this tutorial, we will be working with a publicly available clinical data set that is quite decent in size, but it focuses only on diabetic patients only, and also it is not very regionally diverse. So while it was collected by hospitals and is not very regionally diverse. Okay, so bear that in mind as you see some of the results. And I think that at this point, we can actually let me continue and then until the breakout groups, and maybe let me then transition to manage it after breakout groups. Okay, so as I mentioned, we will be working with a clinical data set of hospital readmissions that was collected over a 10-year period for diabetic patients across 130 different hospitals in the US. Each record represents the hospital readmission record, admission record for a patient that was diagnosed with diabetes and whose stay lasted between 1 and 14 days. The features that describe each encounter include demographics, diagnoses, diabetic medications, as well as number of visits in the year preceding the encounter, as well as some payer information. Remember, in the United States, the role of insurance cannot be understated. There is still a vast fraction of population that does not have health insurance. And so these are very relevant information, as well as whether the patient was readmitted after release and whether readmission occurred within 30 days of the release. We would like to develop a classification model which decides whether the patients should be suggested to their primary care physicians for an enrollment into the high-risk management program. The positive prediction will mean recommendation into the care program. And so here we are reaching our first decision point that will have some fairness implications. The readmission within 30 days can be viewed as a proxy that the patients needed more assistance. And so we're going to call that as a label that we wish to predict, right? But this might have been a little bit of a disagreement. So we'll pay closer attention to it a little bit later on. But just to remind you, just like with my policing examples from earlier in the talk, when the number of arrests is not necessarily the same as criminality, we will need to be careful about whether this readmission within 30 days actually matches the healthcare needs of patients. The second thing that we will do later on is, because of the high class imbalance, we will be choosing as our performance metric balance accuracy. And besides looking at variable balance accuracy for the to assess to assess how well we perform in predicting those that have the healthcare need, we'll be also looking at how many patients are actually recommended for care. And this is we'll be referring to this characteristic as a selection rate. In other words, because there are some resources associated with these recommendations, we'll be using also this additional metric of selection rate, which what is the fraction of patients that are recommended for this extra care. Now, when we're making these decisions in practice, we would be definitely consulting the healthcare professionals that will be using the models further down the line. Okay, so these two bullets is something that we best utilize to bring in those as well as possibly other stakeholders, such as folks that have been using these programs in the past, or perhaps who were denied these programs in the past. So as we're defining tasks in this manner, then some of the fairness considerations are, as I mentioned earlier, first off, which are the groups that are most likely to be disproportionately negatively affected. And in particular, the previous work suggests that groups with different race and ethnicity can be differently affected. Okay? The second question to ask when we're thinking about fairness is, what are the harms? The key harms here, since we're allocating this extra service, are allocation harms. And some of these harms are caused by the event of false negatives. In other words, if we do not recommend somebody who is being readmitted in our data set, right? And so this is a false negative. And this constitutes a harm of not giving the care of somebody who we believe would benefit from it. And then the third question, into which we'll be digging into all this a little bit deeper shortly, is how we should be measuring those harms. So now, to wrap up our kind of very first block of the tutorial, we will try to have a little bit of discussion in a small breakout groups. And so what we will do next is I'm going to put a link to a chat in I'm going to put a link to a Google Meet in the chat, because we figure out that that's actually the easier way to make this work. So you don't need to. So you can keep your AirMeet tab open as you switch to the Google Meet. But so what we will do is once you join the Google Meet, I'll split you up into groups maybe of size 5. And I would encourage you to just kind of make a quick round of introduction and then discuss these two questions. So I gave you examples of how we're thinking about the harms as well as which are the groups. So I would like to discuss where you believe the choices I made are appropriate and how you might go about something like this more generally. Okay. So and after 20-30 minutes, we'll come back. And when you split into these groups, just kind of make sure that one person within the group is tasked with like taking quick notes. And afterwards, maybe I'll do a little debrief when I ask folks if there is something interesting that came up in the conversation. Okay. So I think at this point you can hop off there into the Google Meet, and I will hop off there as well. And once then we can reconvene here. Okay. And when that's over. I see people trickling back in. Welcome back, folks. Let's while we're waiting for for others to trickle in, those in the breakout groups, like if was there any interesting any points that you would like to raise, if you can do so in the chat, so I can that way the folks from other breakout groups can see that. Let me give folks a couple more minutes. I see some Christine says about how the lack of insurance might influence what it means to be readmitted within 30 days. And there was another example drawn from the voice recognition systems that not properly taking into account accents will can impact the performance for different people. I see from Niels commenting out something quite important, which is that how hard can be disentangle the kinds of harms. So that in a sense, perhaps the harms, like the whatever you put it in those three categories, like it may be one way to think about it is just think about it as an opening, a way to kind of get going in terms of enumerating any possible specific harms, even if they might not fall neatly into one of the categories. And Lisa is bringing up something quite interesting about how about how different how the diverse people can experience different kinds of harms, and so it's important to have diverse people present when we're thinking about what are the harms to consider. Okay, folks. So in terms of the next steps, I think that we will now take a break. We will take a break. What about taking it until like 11:15 Eastern time, which would be 10:15 until 10:15 Central time, and then we'll resume with the next session. Okay. so people have a chance to just get refreshed, and so far, and then we'll really jump into things Python, and we'll start going through notebooks. So this was a way how to kind of overview, get our brains going. Okay, so I'll see you in 10 minutes or so. Okay.
Okay, so it is 11:15 a.m. Eastern Time, 10:15 a.m. Central Time. So hopefully people are getting back from the breaks. Um, so welcome back, everyone. My name is Manajit Nandi. I am a data scientist at Microsoft Research, and I will be walking you through this next section of the tutorial. And so in this section, we're going to actually start exploring the data set and start doing some Python stuff. And so if you're running the tutorial from the Colab notebook, be sure you run the installation of the libraries at the top and also import the necessary packages. As a caveat, if you are also running this locally through like a Jupyter notebook, you might have some issues running the model cards, but that's okay because this is more so an optional section, but we'll be able to see what the outputs look like on my screen. So please make sure you import the libraries if you haven't done so, and let's get to it. Actually, can you all see my screen? Yes, no, maybe? Okay, yeah. Sorry, I have the AirMeet open. Can't see the AirMeet while I'm presenting, so let's start with it. So in this section, we're going to be talking about the task definition and the data set that we'll be using for this healthcare scenario. And when you try to design any AI system, there are really two big critical decisions you make. Not to say there's only two critical decisions, but there are at least two critical decisions that you make. First one is, how do you define the machine learning task? What problem are you trying to solve? What are you trying to optimize? And the second decision is, what data sets are we going to use to train the machine learning model? And the thing about these is these are not two different questions. These choices are often intertwined because the data sets we often use in machine learning problems are more so chosen on convenience and availability. We don't choose the best possible data set for some definition of best. We usually choose a data set that is accessible to us or easy to access. And that results in a specific choice of a label and a performance metric. And it's also the case with us, where we chose a publicly available data set that's not necessarily the best data set for the thing we want to model. And in this part of the tutorial, we're going to load the data set, and then we're going to explore it, examine and explore it for a variety of fairness-related issues. The three types of issues we're going to focus on are sort of sample sizes of our different demographic groups, in particular, different racial demographic groups. Next will be the appropriateness of our choice of label. And so in this problem, we'll be focusing on predicting this readmission within 30 days, and we'll be exploring whether that's really the label we want to focus on. And then finally, we'll be looking at sort of the representativeness or the informativeness or the usefulness of the different features in our data set for different demographic groups. And when we're talking about data sets and fairness related issues, besides focusing on just the data set characteristics, we also want to think about how the data set was collected. Was the data collected with the informed consent of the individuals in the data? Were they told that their data is being collected? Did we respect their autonomy? And did we provide them a way to opt out if they feel uncomfortable with the process? And as we explore these data set related issues, we can sort of systematically document them through this data sheets practice. I'll touch on this a bit later in this section, but by documenting our understanding of the data set and also any potential issues we find, we can then communicate any concerns we have about the data and highlight these downstream issues that may arise during the model training, the evaluation process, or even after the model has been deployed. So first thing we're going to do is load the data set and review the columns. And so as a key thing is, we will actually be working with a modified version or pre-processed version of the this healthcare data, this diabetic data set. This data has been pre-processed in order to make it better tool for this tutorial. The full pre-processing code is available on the GitHub repo, and you can see like the pre-processing steps we've done. So we're going to load the data, and then we can explore some of the columns in the data set. And so this gives you a sample of what the data looks like. So each row represents a patient who is admitted into the hospital on a diabetes-related diagnosis. And we can see we have things like demographic information, such as race, gender, age. We have how many days the patient spent in the hospital, along with some quantitative information such as number of lab procedures provided. And finally, we also have whether the patient was readmitted within 30 days. And so with this data set, we can also look more so like what the different types of columns we have. So like I said, we have these demographic features. We have features related to insurance information. And this sort of came up during my breakout group that, oh, hey, insurance status may affect your likelihood of being readmitted into the hospital in 30 days. If you don't have an admission, you might try not to return back to the hospital. And also, insurance status may be correlated with other things such as socioeconomic status. We also have some information about prior hospital visits in the previous years. So did you have emergency room visits? Did you have inpatient day visits? And then we also have the label of whether you're readmitted within 30 days, whether you're readmitted at all, or just general readmission status. And so this is a example of all the different categorical features and sort of the different categories that exist with them. And so in terms of race, we're since race is sort of the demographic feature we'll be focused on, we sort of have 6 different racial categories in this data set. We have Caucasian, African American, unknown, Hispanic, other, and Asian. In gender, we have male, female, unknown. And for age, we have over 60 years, 30 to 60 years, and 30 years and younger. And so now we're just going to do a little bit of processing of the data frame. And so we're going to mark our categorical features. And so the first thing we want to think about when we want to assess a data set for fairness-related issues is sort of these demographic group sample sizes. And from the perspective of fairness, we really care about the sample size of the different demographic groups because it has 2 major implications if we have small sample sizes. One is just general assessment. It's really hard to measure the impact of the AI system on smaller groups just because we have less data points. We're going to have much more uncertainty or error bars around our estimates for these different demographic groups, or also the amount of harm or unfairness we're having for these different demographic groups, but then also on the model training process. Because we have fewer data points for these different groups, the model may not fail to properly learn any patterns specific to these smaller groups. And this could be a really big issue if you're using machine learning models such as deep neural networks that really require a large amount of data points in order to converge to a proper solution. And so with these smaller sample sizes, we will then have lower, or we can expect to have worse predictive performance on these groups. And so now let's explore the data set with respect to our different demographic features. First, let's look at race. And so let's explore the different racial values, racial categories in our data set. We can run this, and then we can also visualize these results as a plot. And one thing we can see is that this data set is heavily skewed towards Caucasian individuals or Caucasian patients. We see that about 75% of the patients are Caucasian. The next largest racial group is African American, which makes up about 19% of the data set. And then the remaining racial groups, unknown, Hispanic, other, and Asian, really compose about 6% of the data. So this data set is heavily skewed towards Caucasian patients. Next, let's explore the data set by the gender feature. So once again, we can run these cells, which will then give us the value counts by different gender groups. We can normalize this frequency. And what we see in this data set is that gender is effectively binary, and we also have no information how it was operationalized, with both with male and females both being about 50%, with females being 54% of data, and males representing 46% of data. We only have 3 samples of data points in this data set that are labeled as unknown or invalid. And so now we're at this point. We noticed, okay, we have very imbalanced sample size in terms of race, and we also have this gender group, unknown, invalid, which we have very little data points for. What do we do with this? And so when the data set lacks the coverage of these different demographic groups, like going by what I said above, it may mean we're not able to reliably assess any fairness-related issues. And thus, there are a couple of interventions we could do in order to address this problem. One thing we could do is collect more data. And so for those groups where we have fewer samples, we can collect more data points for that group. Next thing we could do is bucket the groups together. So taking some of the smaller groups, we can sort of bucket them together. And then finally, we can drop some of the small groups. And the choice of which strategies we use, and we don't have to use just specifically one, we can use a combination of these strategies, depends on our existing understanding of which groups are at the greatest risk of harm. In particular, if we pool different groups together with widely different risk, we could sort of mask the extent of harms. If we pool different racial groups together, we could sort of mask the way that those different racial groups experience harms in the healthcare system. We also generally caution against dropping smaller groups, as this leads to this representational harm of erasure. If you remove these individuals with these smaller individuals, such as by gender, and so that you make gender binary, say male and female, you sort of erase the non-binary or gender unknown individuals in this data set. And key thing is that if you do employ any of these strategies, I think it's important to document or explain in the data sheets or some other document why you made those decisions. And so in our example, we're going to follow two strategies. We're going to merge the three smaller racial groups together, Asian, Hispanic, other, into one bin of other. And this is following the papers Strack et al., which this data set came from, but also retain the original racial groups for any auxiliary assessments. And then we're going to drop the gender group unknown invalid because the sample size is so small that there's no way we can do any sort of meaningful fairness assessment. And so here we're going to run this this cell, and this is going to drop all individuals with gender unknown invalid. And then we're going to bucket the racial groups Asian, Hispanic into other. So I think I'll stop and pause for questions at this time. Are there any questions?
Yes, perfect timing. So Bob asks, what does small mean? Relative to data size, relative to demographic proportions, or relative to disease prevalence?
That is a very good question, Bob. So I think small would usually refer to, so I think in this case, like small, we chose small being 3, in the sense like, usually when you take about statistical sampling, they usually say you should have at least 20. So in this case, we said small because it's less than 20. And so there's no way for us to get any sort of meaningful assessment. I think in other cases, small could sort of refer to the proportion of the data. So for example, if you have like less than 1%, you might not be able to generate any meaningful sample of that. But I think it's very dependent on the context. But then there's some like hard truths where it's like, hey, if you have less than 10 data points for this one particular demographic group in a scale of 10,000 data points, then that just is small by the inherent nature of it.
No other questions in the queue, but maybe wait a few more seconds.
Okay.
Okay.
And so at this time, we're going to do a quick small exercise just to get our brains warmed up, because it's either 11:30 a.m. Eastern time or 8:30 a.m. Pacific time. So maybe your brain's not fully awake yet. And so this is a quick exercise of just explore the distribution of age in the data set, of the age feature within a data set. And so I'll give you a minute to do that. And so if you're following along the notebook, you can just create a small cell. If it is a bit too early in the morning, you can just scroll down a bit and you can see the answer. Have any questions come in while we wait?
Nope.
Okay. So I'll give us about 30 more seconds. So for those of you following along the notebook, you can sort of just play around and look at age, either by referencing some of the code from above or by doing your own analysis here. Okay, so let's explore the distribution of age in this data set. And so we can sort of do the same thing as we did above, where we just run these value counts on this age feature, and we can see that the data set is heavily skewed towards older individuals in the sense that in the patients who are above 60 years and older make up the most common age group in this data set. And although we're not going to be focusing on age-based or fairness-related harms in this tutorial, when we create the data sheets, we do want to document this age imbalance in the data set. And so we do see that older than 60 individuals compromise about 68, 69% of the data set. 30 to 60 years individuals constitute about 30% of the data set. And then younger than 30 constitutes about 2% of the data set. And so now we've looked at the distribution of our different demographic features. Next, we want to really further interrogate our choice of label. So in this part, we're going to sort of dive into this question of whether our choice of label, that readmission within 30 days, really aligns with our end goal that we want to solve, the end problem we want to tackle, which is how can we identify patients who would best benefit from this care management system. And so a framework will be used to tackle this problem is called measurement modeling. And this is based on this paper, Jacobs and Wallach, 2021. And the goal of measurement modeling is to sort of describe this relationship between what we care about and what we can measure. And so if any of you have backgrounds in the computational social sciences, you might have heard this idea of construct and construct validity. The heuristic being this is that in the social sciences, things that we care to study, such as happiness or some of these abstract constructs that we can't directly measure. And in order to really study these things, we sort of need to operationalize them in a way we can measure. So going back to this idea of happiness, sort of happiness is this abstract construct. How can you measure happiness? We can ask people, how happy are you on a scale to 1 to 7? You could maybe directly measure this idea of like serotonin in the bloodstream. Or we can ask them different things like, have you ever had negative thoughts within like the last 7 days? And that gives us some idea or some measurement about the general happiness of the person. And so the context of our healthcare problem, the unobservable construct we want to measure is who will receive the greatest benefit from the healthcare management program. And how do we sort of choosing to measure that? Well, we choose to measure that as whether the patient was readmitted within 30 days from their release of hospital within the absence of such a healthcare program. And so in our case, our measurement sort of coincides with this choice of the classification label. And by operationalizing this construct, when we operationalize the construct, we have to sort of make specific assumptions. So when we say that we're going to measure greatest benefit from the healthcare management program by readmission within 30 days, we have to make certain assumptions. And the key assumption is that the people who are readmitted within 30 days are the patients who are the most patients who are readmitted within 30 days are the ones who would most likely benefit from the this healthcare management program. And so how can we check whether this assumption is true? How can we check that whether our assumptions apply? And so this question is like, how do we sort of establish construct validity? And so if you read this full paper, Jacobs and Wallach, they talk about different ways you can sort of measure construct validity. How can you discuss whether that measurement is really a valid representation of your construct? And this looks at things as like, does the operationalize and capitalize all the things it's supposed to be measuring? Does it look plausible? And does it correlate with other measurements of the same construct? So does our choice of label, readmission within 30 days, correlate with things we expect it to be correlated with? And for the purpose of this tutorial, we're going to really focus on one aspect of construct validity called predictive validity, which refers to the extent which measurements from the measurement model are predictive of measurements of any other observable property. And one key note is that these predictions do not need to be chronological. Therefore, we don't need to necessarily predict the future from the past. We just need there to be a correlation, and that are not necessarily causal. We just need to ensure that the predicted properties, that the sort of predicted correlations we expect to be in the data are there. And so how can we sort of establish this idea of predictability? So we want to look at our measurement, readmit within 30 days, is correlated with patient characteristic that correlate with our construct of being benefiting from care management. And one such general characteristic is sort of general patient health, that we expect patients who are less healthy to more likely to benefit from this care management program. And so while our data set does not contain full healthcare records for all the patients admitted, it does contain two features that we're going to focus on: had emergency and had inpatient days. The had emergency corresponds to whether the patient had any emergency room visits in the previous year, and had inpatient days corresponds to whether the patient had any hospital but not emergency visits in the previous year. And to establish predictability, we want to show that our measurement, readmit within 30 days, is predictive of these two observable characteristics. And so first, let's plot the relationship between readmit within 30 days and also hospital room visits. And so here from this graph, what we see is this relationship between the readmit within 30 days, our label, and this had emergency room visits. And one thing we do note is that patients who were not readmitted, and so patients who were not readmitted, have a lower rate of hospital emergency room visits in the previous years, whereas patients who were readmitted within 30 days had a higher rate of emergency room visits in the previous years. And we have vertical lines on this graph representing 95% confidence intervals. And so what this means is that we see that, yes, that patients who were readmitted within 30 days, thus patients who would most likely benefit from this healthcare management system, are also the patients who had more emergency room visits in the previous year. And so this sort of confirms this idea that we expect to see, that this readmit within 30 days, which reflects sort of patient health, is correlated with this other feature that sort of gives this idea of patient health. That patients who are readmitted within 30 days and thus benefit most from this healthcare program are also the ones who sort of have lower general patient health overall. We see a similar rate pattern when we use readmit with 30 days in order to predict the rate of non-emergency room hospital visits. And so here we see, once again, that our readmit within 30 days label is highly correlated with this has inpatient days. So patients who were readmitted within 30 days were patients who also had more hospital visits within previous years compared to patients who were not readmitted within 30 days. And so once again, we see this trend that our label readmit within 30 days is correlated with this feature that corresponds to like a lack of patient health or lower patient health. And thus sort of give us more evidence that, hey, maybe this readmit 30 days variable or readmit 30 days label is properly capturing this idea of lower patient health and thus represents patients who then benefit from such a specialized care management program. And finally, we can look at how well readmit 30 days predicts had emergencies when we stratify across different racial groups. And one thing we want to note here is that patients in this unknown racial group had a substantially lower number of emergency room visits in the previous year or in the prior year, regardless of whether they were readmitted within 30 days. This readmission is possibly still correlated with had emergencies, but because we have a smaller sample size for this unknown racial group, the larger error, we have a larger error bars, and thus it's hard to sort of say that this is a statistically different rate between patients of the unknown racial group who had hospital readmissions compared to patients who didn't have hospital readmission. We also see that patients with the racial group African American had a higher rate of emergency room visits compared to patients of other groups, regardless of whether they were readmitted within 30 days. However, we also note that that patients of Caucasian, African American, and others sort of follow similar patterns. Now, when we run this on the inpatient days, we also see a similar trend. once again, we see that unknown for patients with unknown race, that the number of non-emergency room visits is lower compared to the other racial groups in both readmit within 30 days is equal 0 and readmit within 30 days 1. But then for all groups, we do still see this positive correlation between being readmitted within 30 days and also having non-emergency hospital room visits in the previous year. In all cases, we see that readmission within 30 days is sort of predictive of our two measurements of general patient health. And so what is the goal of this entire analysis? Well, the goal of this is to sort of explore predictability and sort of show that, hey, that this idea of readmit within 30 days is correlated with things that we expect to see in patients with lower health, general patient health, and thus is a good label for us to focus on for this machine learning task. In addition, we also notice that patients with the racial group unknown have fewer hospital visits in both preceding years, both emergency and non-emergency visits compared to the other racial groups. And so in this point, we'd probably want to reach out to a healthcare professional to sort of understand like why this is occurring, to make sure that there is no systematic difference in this outcome, or is there some issue with our data collection. And so now in this section, let's break into a small exercise. What we want to do is sort of check for predictability with respect to gender and age. And with this, we want to explore, do we see any differences? And can you form a hypothesis why? And then at this time, I'll also stop for any questions.
No questions currently in the queue.
Okay. So if you're following along with the Jupyter Notebook, I'll give you 2 minutes to sort of work on these exercises. Okay, so let's work on this. So first, let's check for predictability by gender. And so what we're going to do is run this categorical plot. We're going to predict whether the patients had any inpatient days in the last 30 days, with our feature being whether they're readmitted within 30 days. And we're going to stratify this by gender. And so we do this by gender, and we see that there is actually seems to be no difference between male and female patients within the readmit labels, but also we see that same general trend that readmit within 30 days is correlated with had inpatient days, but we see no other correlation breakdown by gender or no special trend by gender. Now let's do it by age. And so here we see this interesting trend that patients who are readmitted, that we do see that there is some relationship going on by age. For example, patients who are readmitted within 30 days, if that patient is 30 years younger, then they are much more likely to be younger compared to the other, or patients who are younger and readmitted within 30 days have a much higher rate of hospital visits within the previous year compared to the older racial groups. On the other hand, when the patient was not readmitted within 30 days, patients who are 30 years younger were less likely to be readmitted into the hospital in the previous years. And so we see this interesting trend that if a patient was readmitted within 30 days, then they have, and they're younger, then they're more likely to have hospital room visits. So now let's explore label imbalance. And so now we've established like the label we care about is actually valid. It's actually something we should be actually modeling and something we should be studying. So let's check the frequency of the values of this label in our data set. And the frequency of the different labels is important because it has various implications for our classification problem. And so some classification algorithms and metrics may not work well with data sets with extreme class imbalance. If the data set is heavily skewed in terms of labels, the model may not be able to properly converge or might learn a sort of trivial solution, such as predicting yes or predicting no all the time. In binary classification settings, our ability to evaluate errors is often driven by the smaller sample sizes of the two classes. And finally, label imbalance might exacerbate these problems due to smaller group sizes when it comes to our fairness assessments. So let's check about how many samples in our data sets are labeled as positives and how many are labeled as negatives. And so here we can see, we look at this result and we see that the target label readmitted within 30 days is heavily skewed towards patients not being readmitted within 30 days. In our data set, only about 11% of the patients were readmitted within 30 days. And since there are fewer positive examples, we will expect to have a larger uncertainty in terms of our estimate of our false negative rate compared to our false positive rates. This means there will be a larger difference between the training false negative rate and the test false negative rate, even if there's no overfitting, just because of these sample sizes. And as a result, we'll be looking at the metric of balanced error rate, which is the average of the false positive rate and the false negative rate. And so we chose the balanced error rate because this metric is robust to the different frequencies of positive and negative examples and labeled points in the data set. Since half the metric of this metric is contributed by the false negative rate, we expect the uncertainty in the balanced error rate to behave similarly to the uncertainty in the false negative rate. And so now let's explore how the label frequency varies by group. And so we see that our label of readmit with 30 days readmission is similar for the Caucasian and African racial groups, but appears to be smaller for the other and unknown racial groups. And so this is consistent with the overall lower, that unknown individual patients with unknown race have a lower rate of hospital visits in the prior year. Is there a question?
Yes. So Matthew asks, can you comment on whether any of the standard methods of dealing with imbalanced class labels, example, resampling or weight loss functions, can also be effective in mitigating fairness-related harm by applying them to other features of the data?
So yes, resampling and weighted can help address this these issues. And when we get to the modeling session later on, we'll actually apply data resampling in order to address these label imbalance in our data set.
No other questions, but let's pause and see if anything comes in. Okay.
And so with this analysis, we see that like I said, the readmission for African American, Caucasian appears similar, but we seem to have lower rates of hospital readmissions for patients in the other and unknown group. But because we have smaller sample sizes, we also have a larger uncertainty around them. And finally, we want to explore these proxies for sensitive features. So in this section, we're going to be focusing on which of our features are highly predictive of our sensitive feature race. And these such features are called proxies. And so in this tutorial, we want to focus on fairness-related issues and fairness-related harms through the lens of impact of the machine learning model on different populations. There are concepts of fairness that seem to really focus on how machine models might use information contained in sensitive features. And in this case, like when those proxy features is sort of use of them is sort of justified in sort of a causal reasoning approach. And in certain cases, such as credit loans, for example, use of certain sensitive features or proxies of sensitive features may be illegal in context. And so in credit loans, you can't use race, and you're also not allowed to use zip code information because zip code is correlated with race. Another reason to understand proxies is because they might explain why we see different impacts, differences in impacts on the different racial groups. And so in this section, we'll sort of go into like how we can identify proxies, identify such proxies for our healthcare scenario. So specifically in the United States, Medicare and Medicaid are two federal and state programs to help individuals pay for healthcare expenses. Medicare is available to U.S. citizens above the age of 65 and also younger individuals with severe illnesses. And Medicaid is available to individuals under the age of 65 whose adjusted income falls below the federal poverty line. So first, we want to explore the relationship between patients who paid for Medicaid and our demographic feature. Because Medicaid is available to low-income individuals and race is correlated with socioeconomic status, we expect to see some correlation between race and paying with Medicaid. And so from this analysis, we do see that there seems to be some correlation between paying with Medicaid and the patient's race. And in particular, patients who are Caucasian are less likely to pay for Medicaid compared to other racial groups. If paying for Medicaid is a proxy for socioeconomic status, then this pattern we do see is sort of aligned with our understanding of wealth and race in the United States. And similarly, we use predictability to check that our label aligns with our construct of likely to benefit from care management program. We can sort of use the same idea of predictability to verify that our features are sort of coherent with another, but the features that we expect to be correlated with one another are. And so in this case, we're going to focus on, based on the eligibility criteria on Medicare and Medicaid, we expect Medicaid to be negative correlated with age, and we expect Medicare to be positively correlated with age because Medicaid is available. Medicare is available to anyone above 65 and older. We expect to see Medicare positively correlated with older individuals, and we expect to see Medicaid negative correlated with older individuals. So we run this analysis, and we do see that yes, Medicaid is negatively correlated with age, that younger individual patients are more likely to pay with Medicaid compared to older patients. On the other hand, we see that older patients who are above 60 and older are more likely to pay with Medicare compared to younger patients. And now, as a small exercise, let's explore the relationship between paying with Medicare and our other demographic features. And so in this small exercise, I want you to perform any analysis that would help you understand the relationship between Medicare, race, and gender in this data set. And I'll also pause for questions at this time.
None of the Q, but if people want to go ahead and type something in now.
Okay, so let's work through these. So first, let's talk about the relationship between Medicare and race. And here we see that there is some relationship between Medicare and race, in particular that Caucasian patients and also patients with the racial group unknown are more likely to pay with Medicare compared to patients of the racial group other. And remember that other is now binning Asian and Hispanic together, and also patients of the race African American. Next, let's explore Medicare and gender. And we see that here it seems to look like that patients with the patients labeled female seems to be higher compared to patients labeled male. But if you look at the scale of this, it's going from like 0.330 to 0.305. And so at first glance, it may look like, yes, there seems to be a statistically significant difference. But on the like scientific level, that difference doesn't really seem to be large in magnitude. This is like a 0.01 difference or 0.02 difference. And so I think it's important to point out because like when you use standard plotting tools in Python, like this matplotlib and Seaborn, for example, that we're using here, it automatically defines the scales. And so just because you generate a visualization that looks like it has a meaningful difference, always pay attention to the scale because the scale can be misleading. Skip this one. And finally, now we've done all this analysis, and so we want to document our findings. And to do this, we were going to go through the datasheets for datasets practice. And so the datasheets practice was proposed in this paper, Gebru et al. In 2018. And so the goal of the datasheets is to sort of understand the mode, is sort of to document our understandings of the dataset, like what motivated the creation of the dataset, how was the dataset composed of, how was the data collected, and are there any recommended use cases, and are there any other like interesting characteristics that we think is worth to know. And in the words of Gebru et al., the goal is to really facilitate communication between the dataset creators and the dataset consumers and encourage the machine learning communities to prioritize transparency and accountability. And I think this is very important because especially in the machine learning community, it's very common practice to just like pull a data set you find off the internet and just run your models on it without really thinking about like what that data set is or where did it come from. And I think it's important to talk about like how is this data set created? Is it something that was meant to do, is there a problem that was meant to solve? And is it also something the creators would say like, no, you shouldn't use this data set for this type of problem? And so in this section, we will also briefly talk about like some of the sections of the data sheets. And so one thing to keep in mind is that like the official data sheet is about 50, 60 questions. And so I'm not going to walk you through how to fill out a 50, 60 question form because, you know, that's not very interesting. But I want to sort of give you a brief overview of like some of the examples of what's in a data sheet. And so things about in the data sheets will ask questions of like, what was the data set created for? Why was it, was there a specific like task in mind it was hoping to solve? And what was it hoping to fill? And then also be things like who created the data set, but then also questions of the composition of like what does each instance of the data set compose of? Is there anything missing? And do we identify any subpopulations? Is there a question?
Yes. So Niles asks, are there any techniques, projects that automate the creation of plots/stats that facilitate conversations around construct validity and other validity checks?
As far as I know, in Python, there's nothing that really helps with construct validity. If you're in the R community, I believe that there are some computational social science tools that help with construct validity, but also building, I just want to, I guess, as a shameless plug, one thing we are talking about in the Fairlearn community is sort of building in tooling to help generate these plots and these visualizations and to help data scientists navigate this challenge of construct validity in their work. And then with the data sheets, we also have sections related to pre-processing. So like how was the data set pre-processed? And like I mentioned at the very beginning, that we did pre-process this, the original data set in order to make it more suitable for this tutorial. And if you're interested, you can go through the pre-processing code in this, which is located in this file in our tutorial repo. And they also think about things of like, what has the data set been used for? And also what could it be used for and what it shouldn't be used for.
Thanks, Manojit. So we are right now at the point where we'll take another break and we set up a poll to get a sense whether people feel like they need a longer break or a shorter break. So please fill out the poll so we have a good sense. You know, I think that if people if 15 break is fine, then we can just do the 15 minutes. If people prefer a longer break, then we can do a longer break. So please fill out the poll so we have a sense. Let's see. Actually, it looks fairly evenly split in the middle. So wow, this is perfect. Like we have like almost like perfect three-way split. So what I suggest is maybe we can let's see. So the maybe we can take a 25-minute break. Let's do 30-minute break. I think that this will allow people to kind of like um yeah or take the average. No, we can't do 22. I'm looking at 22.5, and we have a slight balance towards 30 minutes. Okay.
Mira, one question did come in.
Okay, sure.
So the question is, in assigning race to individuals, how do we account for biracial/multiracial individuals? I know this is a difficult problem, but I'm curious to know if computational social scientists have any strategies, workarounds in place.
So this is a fantastic question. When it comes to the issues of gender and race, if you look at our exercise, we're using the labels that are fairly like at this point that like the labels themselves are somewhat dated given the current discourse around race and gender, right? We see binary gender, we see African American, Caucasian, which we don't use anymore, and these categories are right now like presented as exclusive. So ideally, we would like to allow people to self-identify according to their gender as well as race, and allow multi-select questions. And there is a lot of research around that. Now, however, in medical contexts, there are some other categories that might be more appropriate. And so then there are different attributes that are relevant, and they're related. Some of them are related more to sex, some of them are related to gender. But then again, depending on the specific application scenario, when it comes in particular to gender and sex, that are medically more appropriate categories. When it comes to race, we would like to have people self-identify, frankly, because if from the perspective of measuring impacts, we want to get a sense which communities are marginalized, and so self-identification there is key. So let me at least make a decision around the poll. I think let's resume at 12:30, given that this is direction in which people are going, and what we will do then is we might make some remaining breaks in the thread a little bit shorter. So I think it might be better if people get a break. If you need to if you need to get a meal, this might be a good time to get a meal, stretch out, and then we'll be back at in 30 minutes. 12. So this would be 12:30 Eastern. So 30-minute break. 12:30 Eastern and / 11:30 Central. And just to give you a heads up, in the afternoon session is the in the afternoon session we'll just look at assessment and mitigation, and we will and mitigation techniques. So let's break off and see you in around 30 minutes. Welcome back, folks. Let's wait another couple minutes before we resume. And as a reminder, if you have any questions, feel free to ask either in the chat or also in the Q&A. There's a couple of folks from our team, that are available to answer questions, and we're also monitoring the Q&A. Okay, so let's resume. In the previous part of the tutorial, we talked about some of the some of the issues around fairness. You know, that it can that we should think about the fairness related harms at every stage of the AI development pipeline. And we have dug deeper a little bit into fairness issues at the stage of defining the task, as well as at the stage of data processing and data collection. In the remainder of the tutorial, we'll be examining some further stages of the AI pipeline. In particular, we'll begin with looking at the model training, and then model evaluation, and a little bit of model deployment, since some of these assessment questions that we will talk about later on are related to the model evaluation. So as a reminder, our goal is to train a classification model that predicts our target variable, which is a readmission within 30 days, while optimizing for balance accuracy. This was a performance metric that we identified. Now a key decision point is what kind of model we should train. Should this be deep neural net? Should it be random forest? Should it be logistic regression? And there are a couple of considerations that enter the question. I'm going to focus on two that are related to fairness. The first aspect is interpretability. And there are several reasons why it is important to have interpretable models that are open to the stakeholder scrutiny. First off, it allows the discovery of fairness issues that were not discovered by the data science team. If we have an interpretable model, it also provides a path towards recourse for those that are affected by the model. And also, before we deploy the model, frankly, even before we evaluate the model, if the model is interpretable, we can do a face validity check. In other words, we can do a sniff test to check that the model makes sense, at least at the face value. And of course, this step is highly subjective, but it's actually quite important, because very often in practice, the population to which the model is applied tend to be different from those on which the assessment was conducted. And if the model seems to make sense, then we're mitigating some of the problems. Not all of them, but mitigating some of the problems. Now, as a bit of a flip side to interpretability, sometimes is the model expressiveness. In other words, how capable is the model of separating positive examples from negative examples? How well can it do so given the available data set size? In other words, given that we have a certain amount of data set size, can we come up with a decision boundary well enough using the model that we have? And can we do this? Can we train this model well across all groups? Or is there or does the model need to trade off performance on one group against the performance on another group? So this is related to the model expressiveness. There are a variety of other considerations, such as training time, which will impact our ability to iterate, to come up with a better model, as well as familiarity with this model. Of course, this impacts the ability of data scientists to find and debug the model, and definitely, and then not the least, is the carbon footprint. Of course, like this impacts the Earth climate, and also if we need to be careful not to normalize unnecessarily heavy workloads, because even if our one thing might just have a small impact, the cultural impact might be quite large of the entire community running huge models. Okay. So in our case, we are going to make a choice to use a logistic regression model. And so let's examine this along these two axes. On the interpretability side, logistic models over a small number of variables, just like we use here, are highly interpretable in the sense that that stakeholders can simulate them easily. Now, the models are on the expressiveness side. The logistic regression makes predictions that are described by linear weighting of the feature values. The concern with these models is that they might be too simple. Now, here we kind of have a little bit of an advantage that the previous work that I mentioned, the one that developed this data set, also used a logistic model to predict readmission rates, and it concluded that while a little bit might be lost in terms of expressiveness, this is not the analysis was quite very useful. So the logistic model was quite useful. Okay. And so with that said, with our model choice made, let's train our model. Before training our model, let's prepare our data set for a classification. As I mentioned, our target variable is going to be readmission after 30 days. And while there's a couple of demographic variables, the one that we will be using in our analysis as a sensitive feature, in other words, the feature with respect to which we will be concerned about fairness, is race, based on the considerations from race in prior work. And the labels will be denoted as Y throughout the rest of this exercise, and the sensitive feature will be denoted as A throughout the rest of the exercise. Now we'll do some kind of very standard pre-processing, very simple pre-processing, where we expand the categorical features into 0-1 indicators, into one hot encoding called also dummies. And we will also drop race from our variables that we're using for predicting, as well as any variables that are related to either the discharge disposition. And the reason for this is that sometimes this discharge might be actually into the hospital. And so in that case, obviously, like somebody who is released into the hospital will not be readmitted, and as well as the label. So we'll just kind of drop all of these features. And as a quick sanity check, let's make sure that this worked as planned. And in particular, these are the dummy variables that we created for some of the categorical features. Okay. We'll also split our data into training and test portion. The test portion will be used to evaluate all of our performance metric, but also we'll be able to use it to conduct fairness assessment. And here we will do a half-half split. And this is something you might not be used to from other applications. The reason why we're doing this kind of like a more severe split than you might have seen elsewhere is because we really, really care about fairness assessment, and in particular, we want to be able to conduct a good assessment over of the small groups. And so in this case, half-half is a heuristic how to keep half for training but retain sufficient amount for fairness assessment. Now, I mentioned that our performance metric is balance accuracy. Now we'll be using a variety of training algorithms, at least for the purpose of training. And some of them do not support balance accuracy out of the box. So rather than that being a constraint on us, what we will do, we will resample the data so it has equal number of positives and negatives. So this means that we can use the standard classifiers that just kind of optimize standard accuracy, and they'll end up going after balance accuracy. Now this might have again some implications, because seemingly we have a smaller amount, like lesser data set to train our models. But this is something we'll be able to uncover in our assessment stage if that is an issue. And for the assessment stage, we are not doing any rebalancing. We're just using the original data proportions. Okay, we're not doing any resampling. So there's just like a code to rebalance data set. And so you see now our training data will then be in the arrays X train val, Y train val, and A train val. Are there any questions at this point?
No questions.
Great. So we next save and evaluate this descriptive statistics of the training data set, and it's as a way to annotate some of these decisions that we have made so far. And this is something that will be then entered into the model card later on. Okay. So we can see that this is the distribution of the different groups of the sensitive features in our data. Remember that we bucketed several groups into the other. And these are some of the skews that Manoji talked about a bit earlier. Now, remember that the training data, we subsampled the larger label. And so the training data in the label distribution is even. And now we're looking at the test data set. Here we see that the proportions of different groups according to race. And here we see the skew in the label that we had in our original data set. Okay. So now that we have prepared our data set for training, we will train a logistic regression model. In particular, recall that using scikit-learn. So scikit-learn logistic regression actually it has a little bit of the L2 regularization. So to be more precise, it is the L2 regularized logistic regression model. So we set up our pipeline, which also rescales all of the features to mean zero and standard and equal standard deviation, and we fit our model. We will retain both the score predictions. Remember that the logistic regression model will be both predicting the probability of being readmitted within 30 days, as well as a hard 0-1 predictions in YPRED. It's these hard 0-1 predictions that we would like to use eventually to as a way to decide who should be recommended for the care support system. And as a sanity check, let's take a look whether we're doing something better than random in this case. And so the area under ROC curve of our predictions is 0.63. So this is definitely better than the random one, which would have the value of 0.5, but it's nowhere near the perfect prediction, which would achieve the AUC of 1.0 and which would have the curve going even further up, basically in the right angle. And this is something, so we played a little bit with different kinds of models, and basically, given the data that we have, we believe that this is a very noisy prediction problem. So we are reasonably confident that it would be much harder to achieve better performance here. And finally, remember that our metric of interest is the balance accuracy score. Again, the balance accuracy score of a coin flip would be at 0.5. Perfect one would be at 1.0, whereas the balance accuracy score here has value again 0.59. So again, this is it is above reasonably above the coin flip, but nowhere near perfect. So I alluded to the importance of this face validity check around the fact that the coefficients in our trained model make sense. So let's check these. And again, we see that that patients who were in the hospital in the prior year, so such as those with an indicator had inpatient days set to 1, as well as had emergency, have larger, those are more likely to be recommended for the care. And on the opposite side, we see that certain kinds of diagnosis, in particular when the primary diagnosis was things other than diabetes, might mean that these people are less likely to be readmitted. Okay. And take this with a grain of salt. As I said, this is like a face validity check. And in particular, it is important to recognize that these coefficients are, while seemingly you might think about them as being a proxy for things like feature importance, you should be very, very cautious because this can be misleading. These features are heavily correlated. In fact, like head inpatient days, head emergency, number of education, etc., that there is large amount of correlation. And there is other ways how to explore feature importance, which we will not delve into here. Okay. Any questions before we delve into fairness assessment of the model that I just trained?
None in the queue currently, but I'm not sure if people are typing in now.
So so now that we have trained the model, let's take a look about how to conduct fairness assessment. So we're finally getting to the question: how can we quantify how fair the model is? How can we quantify the fairness? So when we're measuring extent of fairness-related harms, we're really seeking to answer the questions: which groups of people may be disproportionately negatively impacted by an AI system, and in what ways? So this is this is a big question. So let me let me split it up into a couple of steps. The way to think about this is that as a first step, we should identify the harms. As a second step, we should identify what are the groups that might be harmed. The third step is quantify the harms, and the final step is to compare the quantified harms across the groups. So let's take a look into this in a little bit more detail. To identify harms, let me give you an example. For example, in a system for screening job applications, one kind of a harm is when qualified candidates are automatically rejected. In a speech-to-text transcription system, high error rates would be a harm. So these are some of the examples from earlier in the talk. In the healthcare scenario, these are the patients that would benefit from a care management program, but are not recommended for it, experience an allocation harm. And in the context of the classification scenario, we call these false negatives. And perhaps and I mean, as I said, calling it an allocation harm is maybe it could be also be viewed of course, as a quality of service harm. So yeah, so I think that, but because we're assigning resources, we were calling allocation harm for the time being. Okay. The second step is to identify the groups that might be harmed. In most applications, just like we mentioned earlier, we would consider demographic groups, including historically marginalized groups, but also groups that are relevant to a particular application. For example, for speech-to-text, things like being a native or non-native speaker, and as I mentioned earlier, it's important to think about intersections. And for the healthcare scenario, we'll focus on the groups defined by race. And I think there was a question.
Yes. So the question kind of jumps in and says, so this requires the existence of some objective quantitative measure of benefit/harm. This is also a really difficult question.
Yeah, so I think that's a very important one. So for in this talk, we are looking at primarily at the allocation harms and the quality of. So the techniques that I'm talking about here occur in the context of allocation and quality of service. What I'm talking about, I think that I'm not even touching on any of the representational issues where it might be much harder to quantify things. And when we're in the allocation setting, then often the situation might be a little bit simpler, because we can, at least from different angles, evaluate how this impacts the populations, whether they're receiving it or not, and what some of the downstream effects might be. We always have problem predicting anything long term, but at least anything that is shorter term might be included into our benefit calculation. But there doesn't have to be just one metric. And in fact, as we go to this next step, which is quantifying the harms, I'll give examples of a couple of different metrics. But I agree that that's definitely a limitation here. One way how we get around it is that we consider not just one, we might consider multiple different metrics, and that way, we get a little bit of a guardrail. But yeah, it's a simplifying assumption, and we need to be careful. So we should, in particular, go back to this question of construct validity, right? Is the quantity that we're measuring capturing the actual concept, the actual thing that we're after? So let me now give you some examples how we can go about quantifying the harms. Okay. And in this case, we're looking. So, for example, in the job screening scenario, we would be quantifying the number of candidates that are classified as negative, that is not recommended for the job, but whose true label is positive, and they are, in the sense that they are qualified. And you see, there are things lurking, like there is some kind of does our label as positive actually, actually match the idea of being qualified? And so in this case, one possible metric would be the false negative rate, fraction of qualified candidates that are screened out. In speech-to-text scenario, and generally in some of these quality of service metrics, we could be measuring harm by word error rate. So in this case, this means number of mistakes in a transcript divided by the overall number of words. And so in this case, this is basically the same metric that we would use for the performance of the overall system. Now, in the healthcare scenario, we think that there are two we in the remainder of the exercise, we'll be thinking about two metrics for quantifying harms and benefits. The first one is false negative rate. That is, what is the fraction of patients that are that are in our data readmitted within 30 days. In other words, they are underlying positives, but they are not being recommended for the care management program. Okay, and so this is one way how to quantify our harm. Now, in addition to that, we will be also tracking a selection rate. There's the overall fraction of patients that are recommended for the care management program, regardless of whether they are admitted within 30 days or no. So in a way, this is one way how to quantifying the benefit. And the assumption is that all patients might benefit similarly from the extra care, right? So this assumption is, of course, not perfect, and so we need to be examining both of these issues. There is another reason why we might include something like selection rate in addition to false negative rate. So remember, when we were defining label, we were really concerned how well it matches what we're truly after. And so, because like our labels, readmission within 30 days is not necessarily a perfect predictor of whether patient would benefit, we're using this selection rate as an auxiliary metric. We'll be tracking both. So for simplicity, we'll be considering these two. But if you can come up with other metrics that perform either downstream benefits or downstream harms, then you could also include them in the assessment. Now, the fourth step is to compare the quantified harms across the groups. And the workhorse of such a comparison are what we call disaggregated metrics, which is just a long name for something that's very intuitive. These are just the metrics that are evaluated on slices of data. So for example, if we want to measure harms due to errors, like in the speech recognition system, we would begin by evaluating the error on each slice of the data. And if some of the groups are seeing much larger error than the others, we would flag this as a fairness harm. Now, when we have a certain metric and we evaluate on all of the groups, sometimes we might want to summarize it in a single quantity. There are different ways how to summarize this. One of them would be the difference between the largest and the smallest value. It could be the ratio of the values between the best and the worst slice. And in certain settings, such as we might want to just kind of guarantee a certain minimum quality of service, such as in speech recognition. In that case, we could also report something like worst performance across all considered groups. For example, if we're working with our example, and I'm not quite sure whether our data will match exactly, but just for the sake of an example, we have 4 slices here. The folks that are annotated as African American, Caucasian, other, and unknown in our data, for all of them we measure the false negative rate, and then we get to report. So first off, we can see here that, for example, for the unknown group, the false negative rate is above 0.5, right, as is for other, right? So that tells us that our system is performing much worse there. And also we can measure the difference between the rates, between the largest number, which is unknown, and the smallest number, which is in this case African American, which is 0.24. If the largest difference is 0, then all of the groups then would be on average experiencing the same level of the benefit as quantified by this metric. Similarly, we can be looking at the smallest ratio, the ratio between the smallest and the largest. Here, the ideal value would be 1, or we can be looking at the maximum or worst case value of the metric. Okay. And we would typically not be, even if and one thing to keep in mind, even if the value of the metric is 0 or 1, even that does not mean that the system is fair. It just means that along one axis, along one kind of data set, it does not exhibit the discrepancy. It does not exhibit disparities, right? So we would be careful. Okay. Any questions?
None in the queue, but we can pause.
So in order to in order to kind of allow this kind of disaggregated metric evaluation, we are using the data structure called metric frame, which is part of the Fairlearn package. So So let's use this metric frame to assess this train logistic regression classifier for fairness-related harms. Now, in its simplest form, you just take the metric frame takes 4 arguments. The first argument is a metric function, which is a signature similar to following scikit-learn convention, where you give it a y true and y pred. False negative rate is one of the metrics provided in the Fairlearn package. Then it takes the labels. It takes predictions, and finally it takes the sensitive feature, which in our case is race. And the metric frame, and once we initialize this, then we can check what are the values on each group. Okay, so in this case, we see the values where they are similar to the table that I was showing you above. Metric frame also has methods that allow you to quantify this difference ratio as well as the worst case performance. And so I'm going to show that here. Again, difference is the difference between the largest and the smallest value. Ratio is the ratio between the smallest and largest, right? So ideal difference would be 0, ideal ratio would be 1, as well as the worst case. In this case, since we are going after the false negative rate, the worst case is max. Now, instead of just kind of like in addition to just evaluating a single metric, you can also evaluate multiple metrics. For example, in that case, you can create a metrics dictionary, which is just a dictionary from strings to different metric functions that have the same signature as the one that I described, standard scikit-learn signature. And in this case, we'll be tracking selection rate. This is one of the metrics provided by Fairlearn, as well as false negative rate. This is also a metric provided by Fairlearn, and balance accuracy. This is a standard scikit-learn metric. So we just kind of imported balance accuracy score from scikit-learn. Again, where we just kind of initialize our metric frame object, but in this case, for metrics, rather than providing just a single metric, we provide this dictionary and still supply the labels and predictions, and finally the sensitive feature. And what we see if we just kind of look at the by group field, we see a data frame that summarizes the results. Okay. Now we see that this unknown group is somewhat different, right? Like this is the group that gets selected at a smaller rate and also is experiencing the largest false negative rate. It is also the group that is actually experiencing the worst balance accuracy, right? So along both the allocation harm axes and something like quality of service axis, which is what was the accuracy for that group, it is experiencing the largest harm. Of course, we can also do the difference. In this case, the difference is a pandas series. So in this case, we get the difference between largest and smallest for each of the metric. So for selection rate, this difference is 0.137, for false negative rate 0.242, and for balance accuracy 0.06. And of course, I think they might be nicer to view this transposed. And again, similarly, as the difference is returning this series, the ratio is also returning series as well. Group min and group max are returning the series. Okay. So there's a way how to view these summaries of these metrics. And because we are returning the pandas data frame, we get to use some of the plotting functionality from pandas. In particular, what we can do, we can plot this data frame using a bar chart. Across all metrics, we'll be using subplots. Since we have 3 metrics, we will be using layout 1x3. Let's make sure to run this and then walk you through this. And I'm choosing the figure size that makes things work well for us. We don't need a legend, and we're rotating our labels by negative 45 degrees. And we're doing a little shift so they are nicely aligned with these with these bars. Okay. And again, what we see is that in terms of selection rate, that is the fraction of individuals that would receive the care, unknown receives the lowest care, while unknown has the largest false negative rate. and the worst balanced accuracy. Now, remember that we did not include a race in our in the model that we're training. And so just because we did not include the race in particular, note that it does not mean that our model will automatically then not somehow impact people from different racial groups differently. Okay. And there could be a couple of reasons why this happens. For example, it could be that there is not enough instances from that group. We know that it's also the smallest group, and or it could be also that the actual feature distribution itself differs across the loops across this group, and so the features are not equally useful or for the that we have for predicting who will be readmitted in this group. Okay. Now, we are not going to dig deeper into why this is going on. I'm just going to call out that the real-world application often exhibit both kinds of issues at the same time. And maybe time to ask another question.
Yes, there's one question in the chat. Anna asks, could you restate what balanced accuracy shows?
Oh, what the balance accuracy plot shows here, for example. So remember, so balance accuracy looks at what is the accuracy that our system achieves on the subset that has label positive and label negative. So basically we are looking at the accuracy on the rebalanced data set. And this is our performance metric with respect to we are training to maximize this metric. So balance accuracy of 1 would be perfect, and 0.5 would be a coin flip. And so basically what would we see here is that from the perspective of performance, so not from the perspective of harms, this is like how we're deciding to quantify performance of our system, we still see some amount of disparity, and in particular, the unknown group has a smaller value of balance accuracy. So I'm not sure whether it answered the question, but balance accuracy is the simple average of the true positive rate and true negative rate. So, okay, cool. I saw one, so I'm hoping that means that it was answered. Great. So what I'm going to do next is, as a quick exercise, let's try to.
Oh, Miro, there's just one question that just came in. Davida asks, I assume these metrics-based approaches work better to assess fairness with sex/gender questions than race-based questions because the categories, male-female, are better balanced. They are closer to a 50-50 split. Of course, this neglects non-binary.
I see. Sorry. Like no, actually, like, I'm glad you're asking because this is a different kind of balancing that I'm talking about. So look at our sensitive group that we're looking at is race, and we have 4 buckets. You know, they are imperfect. They're like, but still, we're looking at 4 different buckets. So in particular, we were thinking about gender. We would most likely be considering men, women, non-binary, and prefer not to tell or something like that, right? We would still be considering something like possibly like 4 different buckets. But this balancing that I'm talking about is balancing of the label. So we're doing binary classification into who should be provided care versus who should be recommended for care versus who should not be recommended for care. And so basically what we're looking at is like we're balancing the 2 different kinds of error, that is false positive and false negatives. So our performance metric here is driven by the fact that the classification problem is binary. But the groups with respect to which we are evaluating fairness don't need to be just kind of binary or binarized groups. So in particular, like throughout this exercise, we are looking at the sensitive features with that is split into 4 different buckets. Great. And so in particular, what we're doing for balance accuracy here, right? We're looking about like when within the folks labeled as African American in the data, what's their balance accuracy if we rebalance the underlying positives and negatives within this subpopulation. Okay. As a quick exercise, let's just try to see how this would work on other fairness unaware models. And I think in the interest of time, what I will do is like I will slowly go through this exercise rather than and it's to make sure that we hit other points in the tutorial. And later on, you will have access, of course, to this student notebook that you'll be able to fill in yourself as a little sanity check. Okay, but I'll be walking through it slowly. Okay. So in this exercise, what we will do, we will conduct a fairness assessment of a different model. In this case, we will train a model that is using gradient boosting. So in particular, this model that might not be as interpretable, but might be more expressive. Okay. In this case, to fit the model on the training data, we train it on exactly the same way as before. But remember that our target metric is balance accuracy, and so that's why we will be training it on the let's see, on the balanced data set. And remember, this balancing is with respect to the labels, not with respect to the group sizes. Okay. And we will also capture the predictions on the test data. So while this is running, let's think about the metrics that we'll be evaluating in also using the metric frame. We'll be looking at 3 different metrics here. First of them is the count. In other words, what is the number of data points that belongs to each category of sensitive features? This is an important metric to track because it gives us a sense of how confident we should be in these statistics. And then here we'll be looking at false positive rate and recall score, just as a way to exercise things. Okay. So count is just a very simple metric that has the same signature as required for scikit-learn, but all it does, it really just kind of counts the number. It returns just the size of the provided array. As I mentioned, we have imported the false positive rate from Fairlearn, and recall score is a standard scikit-learn metric that we will that we can just list here, and we've also imported that above. For metrics, when I want to evaluate them, remember that the metric frame takes these 4 attributes. For the metrics, we can either provide a single metric, and in this case, we want to look at a multiple of them, so we'll provide the dictionary that we have just created. The true labels, remember, we're evaluating on the test data. And our predictions were saved in the exercise _pred. For sensitive features, let's first try it with race. So let's initialize the metric frame for the evaluation by race. And then, as before, we will first examine the data frame of the disaggregated metrics. So we're just going to examine the by group field of the metric frame that we just calculated. And again, we see here the different categories of race in the rows, different metric names in the columns, and the values. And so remember, we see that as we were discussing earlier, Caucasian is overwhelming, and unknown and other are the smallest groups here. And of course, we can also run the plot command here. And the key part here is to enable subplots, and then we have chosen some convenient layout figure size, as well as rotation and position. So this is the same one as we used before.
So there's a question in the chat from Bob. Can we pass in a data frame of sensitive features instead of just a series?
Fantastic. Glad you asked. Indeed, we can pass it both race and gender. And in this case, of course, like my beautiful design will not work, but it still works. So let's run this. So in this case, we can select both race and gender. And what we get is kind of what you expect, right? So here you get like the hierarchical column index with the now the metrics evaluated on these intersectional slices. And in this case, I think my beautiful layout probably, I think it'll be a little bit cramped. So let me just try to do it slightly differently. Let's see how well this will work. Okay, maybe it doesn't have to be quite so wide, right? Okay. And well, unfortunately, this ended up being at the bottom. So basically here, at least like with the basic functionality of the data frame, I think we would need to make it a little bit smaller. You get still this performance with the, but in this case, for the intersectional groups. Okay. One thing that, okay, sorry, are there more questions?
Nope, that's it for now.
Now, I mentioned that that when we have a small, like we have a large variety of the counts of the data set size of the different slices, and so in particular, when the data slice, some of these are much smaller, and so for these we should be much more. In a sense, like our metric values are much less reliable, and so in the section that we will not go through, but you can go through separately, we show how it is possible to use metric frame to add error bars to all of these quantities, so you have a sense of how reliable these numbers are. Okay, and I think that at this point, what I'm going to do, I'm going to switch over to Manojit, and maybe we can take a very quick break, just 2-3 minutes. But I think that in the interest of time, I think we should just switch and continue. Okay.
Miro, I see there's a quick question in the chat again. So Christine asks, how do you trade off between different models when one is more fair but less accurate and another is less fair but more accurate?
Yeah, so we will circle back to that a little bit later, but as a quick heads up, like in some of the experiments that we have seen is this actually might not often be the case, and sometimes when the model that looks ever so slightly more accurate on your even on your test data, on your assessment data, might not be as accurate once it's deployed, or these differences between the models might not be as strong, because once the model is deployed, basically the population is often slightly different and shifts over time, etc. So that's one thing. The second aspect to keep in mind is that, like, yeah, it's a hard question, and ultimately it's a question of prioritizing different metrics, and this is something that there is not like one answer that will work for it all. I think the main thing that I would just kind of encourage you to think about when you run into those settings is, besides the question of prioritizing, so what does it matter, like how much it matters in this context for us, how severe are the harms that we're seeing versus like the possible benefit of slightly better performance, bottom line for us, for the company, so doing that prioritization decision. Also keep in mind that the population on which you will be rolling it out might be somewhat different than on which you're evaluating it. So those differences taken with a little bit of grain of salt. Okay.
Okay. Can everyone see my screen? Yes. Okay, great. So thank you, Miro. And so in the previous section, we trained a logistic regression predictor on a fairness unaware model, and we found that there was a pretty large difference in the false negative rate between the groups. In particular, the unknown race group had a much higher false negative rate compared to the other racial groups. And now in this section, we're going to sort of look at mitigation strategies. How can we mitigate this unfairness issue that we found in the above section? And so right now we have trained a machine learning model, but we want to keep one small caveat is that we don't want to focus our unfairness mitigation techniques to just the training and testing stage of the AI lifecycle. We could actually have introduced mitigations earlier on, such as checking for constructability or by collecting more data. But now we're in the model training stage, and we want to mitigate these unfairness-related issues we found in our machine learning model. How can we approach this? Well, there are really three common families of mitigation strategies when it comes to the model training stage. First is pre-processing. So a pre-processing mitigation algorithm is one that is applied to the input data to the training algorithm. And so for example, some strategies seek to remove dependencies between the input features and the sensitive features. So if you have your X, you have your sensitive features, and you try to like decorrelate them. You could also apply mitigation strategies at training time. So the model is trained by some optimization process. What if you modify that optimization process in order to satisfy some fairness constraints? So it's not, hey, just optimize for accuracy, it's optimize for accuracy subject to this fairness constraint. Finally, we could do a post-processing mitigation strategy. In a post-processing mitigation strategy, we take the outputs of some trained machine learning model and we transform those outputs in order to satisfy some fairness-related constraints. For example, we take the predicted probability of readmission from our logistic regression, and we threshold it according to some group-specific threshold. And we will now, in this section, we're going to dive into two different algorithms to approach this like unfairness mitigation. One is a post-processing approach, and the other is a reductions approach, which is more of a training time algorithm. Both of these are meta algorithms in the sense that they sort of act around as a wrapper around standard machine learning models. So you pass in a standard machine learning model into these meta algorithms, and you get a new classifier that satisfies these fairness constraints. And we hope to do this with this, we hope to make them very versatile and easy to use in practice. So let's talk about post-processing in a bit more detail. Post-processing algorithms are sort of this class of machine learning, these unfairness mitigation techniques that take in an already trained model and the data set as an input. And we want to transform the output of the machine learning model to satisfy those group fairness constraints. They may be, and in various situations where the developer has only access to the outputs of the machine learning model and maybe not the machine learning model themselves for like fairness, for security or privacy reasons. So if you're working like as a government contractor, you may not have direct access to the machine learning model, but you have access to the outputs of the machine learning model. This is a good case where you want to use post-processing techniques. Within Fairlearn, our post-processing algorithm, the threshold optimizer, comes from this paper, Hart, Price, and Cerebro. It was written in 2016. And so how the threshold optimizer works is it takes in an existing, possibly pre-fit machine learning model whose predictions act as a scoring function and identifies a separate threshold for each of the groups in order to satisfy the objective function. And so in this case, we want to satisfy the objective metric of balanced accuracy subject to the fairness constraint of false negative rate parity. And as a result, we're going to produce a new machine learning classifier that is a threshold version of the underlying model, but it now satisfies the fairness constraints. And one key thing about the threshold optimizer is that we require during the training process that all the groups have the same false negative rate parity, or that they have the same false negative rate. And so in order to instantiate our threshold optimizer, we're going to pass in three parameters. One is an existing estimator that we wish to threshold. Next is our fairness constraint that we want to satisfy. And finally, the objective metric that we want to maximize. And so if you're familiar with the scikit-learn API, this may look very familiar to you. So we have our model class. We pass in our parameters. Our estimator is that unmitigated model we trained in the previous section. Our constraint is the false negative rate parity. And finally, our objective is the balanced accuracy score. So now we have instantiated our new threshold optimizer. And one key thing about the threshold optimizer is that in order to use it, we actually have to have access to the sensitive features during both training time and once it's deployed. And so now we've created our threshold optimizer, and we're gonna fit it to the data. And so, like I said, this looks very similar, very familiar if you're familiar with the Scikit-learn API. We have this fit function. We're gonna pass in our balanced training data, our balanced training labels, but we're also gonna pass in our sensitive features, a train bal. And so now we fit the model. Is fitted. And then we can evaluate the output. And so one key thing is that when we call predictions or predict function, we have to pass in the test data, but we also have to pass in the sensitive features for the test data as well. So we pass in X test, and we also have to pass in A test. And then we can create a metric frame around these results in order to evaluate the performance of our new threshold optimizer. Give it a few seconds to run. And now we can compare let's compare the performance of our new threshold optimizer algorithm compared to our original unmitigated model. And see on the left, you can see the metrics performance of the unmitigated algorithm. On the right, we can see the performance of the threshold optimizer. And so here, one thing you will note is that the false negative rate between the unknown group in the unmitigated model was 0.67, but in the false negative rate for the threshold optimizer is 0.43. And one key thing to keep in mind is look how close are these values together. The false negative rate for the threshold optimizer appears to be much closer together. So they're more so centered around this 0.4 false negative rate difference compared to our unmitigated model, which has a much higher false negative rate parity. Next, let's zoom in on the sort of the maximal differences between the two groups. And here we can sort of see a quantification of what I was talking about above. In the unmitigated model, the maximal false negative rate difference was 0.24. There was a 24% difference between the largest and smallest false negative rate. Yet in our threshold optimizer, we only have a difference of 0.06. And one thing to keep in mind is that also if you look at the balanced accuracies for each group, they are more or less roughly the same. And so we've been able to minimize the false negative rate difference parity, so minimize the fairness-related harm, while keeping the accuracy, the balanced accuracy, the same for relatively the same for all of the groups. And finally, we're going to save these results so that we can use them later on in the model card. And now, as a next section, one thing we want to verify is that the threshold optimizer, in theory, should achieve false negative rate parity on the training data set. That means for all the racial groups in our training data, we should achieve roughly the same false negative rate parity. And so here we're going to create a new model.
Hold on, Manoj, I think we're losing your screen.
Oh no!
Or is everybody else seeing it? Just me?
Have you lost my screen?
Yeah, I don't see it either.
Yeah, I don't.
Okay, can you see my screen now?
Yes.
Okay. Right. So with this correctness check, one thing we want to verify, like I was saying, we want to verify that the threshold optimizer achieves zero false negative rate difference on the training data. So we're going to pass in the training data and the training labels into our predict function and create a metric frame around that. And so if you look at false negative rate differences, they are almost very similar. And then we can just look at the differences and see that more or less that the false negative rate difference, the maximal false negative rate difference, is about 1%. So more or less the false negative rates for each of the racial groups on the training data is relatively the same. And so that verifies that, hey, the threshold optimizer has been trained properly. And now, in the interest of time, we're going to I'm going to skim over this exercise a bit. You have access to the notebook, and so you can go through it on your own to fill through it. But the key idea of this exercise is that we want to sort of create our new threshold optimizer and using the constraint of true positive rate parity rather than false negative rate parity. And the heuristic behind this is that true positive rate plus false negative rate should equal 1. And by achieving true positive rate parity, we should, in theory, produce a threshold optimizer with relatively the same performance as our original threshold optimizer. And so I'll briefly go through this. And so we're going to create a new threshold optimizer with the constraint of true positive rate parity. We create that. We train it on the training data. We fit it to the test data. We create a metric frame for our results. And then we compare the performance of this new threshold optimizer compared to our original one. And so we see that more or less the results of these are very similar. I actually had to do a double take because I was like, wait, these are almost exactly the same. But here you can see some differences. But more or less, by changing our fairness constraint from the true positive rate parity versus the false negative rate parity, we achieve roughly the same results. And this is sort of just a heuristic that yes, this makes sense because these two are constraints are sort of corresponding to the same thing. Now, one key thing about the threshold optimizer is that it actually produces randomized predictions. And so what this means is that in order to achieve these like separate thresholds for different racial groups, we are actually randomly predicting between two thresholds for each of the racial groups. So for race equals African American, we have threshold 1 and threshold 2. We flip a coin and we decide which threshold to use. And the key thing about this is that in certain practices, you may not be able to deploy such a randomized algorithm. And as a result, we'd want to create a non-randomized or more deterministic version of the algorithm. And so in the interest of time, I'm not going to really go into too much detail about this, but if you can sort of go through this on your own. But I think it's important to just run these cells just because there's dependencies later on. But one thing we will see is that if you can create a deterministic version of the threshold optimizer, and that deterministic version gets relatively the same results as our randomized version. And so we can get the same performance and the performance gains of our threshold optimizer, which was maintaining the same balanced accuracy while minimizing the false negative rate parity from a deterministic algorithm. And so once again, we see that, yes, we can get relatively the same performances between the deterministic model and the more randomized threshold optimizer. And so this is a very important caveat. If you are in a setting where because of regulation or some other restriction, you are not able to deploy a randomized algorithm. And now I believe I pass it back to you, Miro.
Yes, that's correct. So with the threshold optimizer that Manoj has been talking about, we took a model that was trained in a standard fashion without any consideration around fairness and transformed the model's decision boundary, the model's prediction, to satisfy our fairness constraints. The limitation that Manoj pointed out is that that once deployed, the threshold optimizer just kind of acts as this kind of like a tweak at the top of the model, needs access to the sensitive feature at the deployment time, basically because it applies a different threshold to the score being produced by the base model. Now, in the next, I will tell you about a different unfairness mitigation strategy that we call it the reductions approach. And this is something that I've developed with some of my collaborators, including Hannah Wallach, on the call. And here the goal is exactly the same as we did in threshold optimizer. Our goal is to satisfy some fairness constraints and while optimizing a performance metric, but what we will get are the classifiers that do not need access to the sensitive features at the deployment time. So I mentioned that we are calling these this approach reductions, and the reason why we're calling it that way because it's so on one hand it's a standard computer science terminology, but what it really means is that it's a wrapper approach. But instead of wrapping an already trained model, what we do, we wrap a standard classification or regression algorithm. So for example, the algorithm logistic regression that we used earlier. So in other words, as an input to this reduction algorithm, we're providing the entire object that supports training on some provided weighted data set. Okay? So the reduction algorithm itself receives the training data, labels, as well as sensitive features. On the other hand, the algorithm that we're wrapping does not need, in fact, does not need access to the sensitive features. The goal, as I mentioned, is to optimize the performance metric subject to fairness constraints. The reduction approach that I'll be showing you about is called exponential gradient. The way what it does under the hood is that it creates a sequence of reweighted data sets and then retrains the wrapped model, such as logistic regression, on each of them. Now, a nice thing about this retraining is that it's eventually guaranteed to find a model that satisfies these performance constraints while optimizing the performance metric. Okay? And in practice, the way you can think about it is that that we train first the model logistic regression model on the original data that has not been reweighted, and then we check, are the fairness constraints violated or no. Based on that, our reduction, our exponential gradient that runs around this, then decides how to carefully reweight the data and passes it again to the logistic regression. Okay, and does so iteratively, maybe for 10 to 15 iterations typically. Now, if we want to train this wrapper model, we give it two parameters. One of them is an estimator. And remember that this is an object that supports training. So we're not passing it a fitted model, we're passing it an algorithm. Okay. And in addition to that, we're passing it constraints. In the case of threshold optimizer, these constraints were just expressed as a string, and we were requiring some metric that was quantifying harms to be exactly the same across all of the groups, at least at the training time. Now, in exponential gradient, we are allowing these constraints to be relaxed and a little bit more general. So actually, constraints is not a string, but an object. And in our case, as Manojit pointed out, we're still after the false negative rate. But but for something that the exponential gradient works with a true positive rate, which is just 1 minus that. And so trying to have a true positive rates that are close across all of the subgroups is exactly the same as having false negative rates that are closed. So we are not modifying our fairness goals at all. We're just kind of flipping our the way we're measuring them. Okay. And while in the threshold optimizer, we're trying to make the values of false negative rate or of true positive rate exactly equal across all of the subgroups, here we're allowing to specify some kind of a slack. In our case, it's the difference bound. Okay. So I went through it quite fast. So do you have any? So maybe now is a good time for a few questions, if people have.
So far, there's no new questions, but let's see if...
Well, let me actually wait a minute if people have any questions. Okay, so let's see. So how do we create this exponential gradient estimator? Oh, I see. Is there a question?
Yes. So Bob asks, what is the rule of thumb for difference bound? What is practically significant difference in false negative rate?
Yeah. So I think that here this one is actually somewhat smaller than needed. So I think that there's two considerations. One of them is purely given that we're assessing our that we have a certain small group sizes, right? And so there is some uncertainties with which we can even evaluate the true positive rate. It definitely is not meaningful to be forcing the difference bound of being exactly zero. Even 0.02 that we're using in this example might be too small. So 0.02 might not be something that we can actually like reliably even guarantee. And so that's one aspect. The second the second reason is that you're alluding to. Okay, so what's a good rule of thumb? And I'm gonna have a similar answer to what when somebody was asking earlier, like basically so what should you choose a model that has a better performance versus like lower versus better is better according to fairness metric. So this is something that is worthwhile kind of translating into to impacts on your population. And very often what we'll see also later on in this like in actually like just a couple of cells below is that we'll be looking at certain trade-off curves. And so basically we'll examine multiple different models that achieves different values of this difference, and then you will make a call basically. And as I said, it depends on the severity of the harms versus like when there's trade-off between the target disparity, the target difference between the extent to which the population are harmed versus any performance benefit possibly from the perspective of optimizing some other metric. So I don't have a clear-cut answer. Okay.
There's also another question by Christine. And they ask, how fast does the system converge on these weights for the inputs to the machine learning algorithm? Not sure if I'm using the right terms.
No, that's a fantastic question. So as I said, you need to retrain the model multiple times. And as you see, I'm retraining it right now. And so I was like, while we're talking, I might as well let it do some work. So definitely it takes, so if the logistic, we need to retrain roughly like in practice, we see somewhere between 10 and 20 times. And so basically, it's roughly 10 times slower. But however, it in our experience, it converges quite well, and it comes with some mathematical guarantees, so we understand that it should converge. And so I'm just going to say that, but otherwise, it is slower. It's roughly between 10 and 20 times slower, and we're looking at a couple of ways how to scale it up should that become a concern. But yeah, in these applications that we're looking at, like it doesn't seem to be quite such a major concern, unless of course you're running a tutorial, and
That's it for the questions for now.
Great. And so we're fitting this exponential gradient model. After the model is fitted, we will then yeah, I could have been a little bit smarter with this, but yeah. After the model is fitted, it will of course like evaluate the predictions on the test data, and then take a look at them using the metric frame. So let's wait another moment. Are there any more questions while we're waiting? If not, then let's continue. So as before, we extract the predictions of the model, and we look at the same metrics as we saw before. And now we kind of see that, like, okay, it doesn't seem like it improved some, but not quite as much as we saw on the with the threshold optimizer. And part of it is due to the fact that that it does not have access to the sensitive features at the deployment time. However, there is some reduction compared with the metric that we saw before. I think before the false negative rate difference was around 0.23, so it's still reduced. Now, the actual classifier that was returned is not the only one that we have access to. I mentioned to you that exponentiated gradient trains this sequence of logistic regression classifiers on reweighted version of the data set. And similarly to the threshold optimizer, then at the deployment time, it randomizes amongst them. And this turns out to be common in many, many different fairness mitigation techniques. And this is an issue, actually, just like Manojit alluded to, is in some deployment settings, the randomization might be complete non-starter. This resulting classifier just becomes much harder to interpret and do any kind of face validated check around this, which is a separate issue. So what we can do instead, and which I believe is something that is maybe a very nice kind of win-win across both axes, that is like not having classifiers that are randomized and having them that are a little bit more easier to interpret, is instead what we often tend to do, we examine the iterates, the individual models that the explanation gradient created over its run. So you have access to this by looking at the predictors, and here you see that there is 12 of them. So in particular, this means that that what we're seeing is 12 times slower than just training a single logistic regression model. Okay, so now what we will do is for these 12 models, we evaluate two metrics. We will evaluate the balance accuracy as well as the largest difference between the false negative rates. In other words, we'll be monitoring both the performance metric in the form of balance accuracy, as well as the fairness metric in form of this difference in the false negative rates. And now I'm going to show you what this looks like. So I mentioned earlier that very often we will need in practice you might need to do the trade-off decisions, and so I'm not going to go through all this code, but instead let me show you what it looks like when you compare all of the different models that we have constructed along the way. Right. So I mentioned so there is the original unmitigated model, which will be denoted in green, the threshold optimizer, which is in red, and then the deterministic version that Manojit alluded to is possible to derive as well in purple. And then there is the combined exponential gradient model, which is in orange, and then the different iterates that are in blue. And on this plot, on the x-axis, I'm showing you the balance error rate, the overall metric, overall performance metric. And of course, smaller is better. So you want to be to the left side. On the y-axis, I'm showing the false negative rate difference. So again, like the ideal value would correspond of 0 would correspond to there being no difference the false negative rates experienced by different groups. And this threshold optimizer results are actually doing very, very well, but they require access to the sensitive features. We see that the unmitigated model has among the lowest balance error rates, but at the same time, it has a large false negative difference. Now, I mentioned that the exponential gradient reduced this false negative rate difference somewhat without sacrificing much in the performance. Now, it turns out that there are other models that might make sense to choose, such as this model 1, 3, 10, perhaps, or perhaps model 9, that have been produced by the exponential gradient algorithm, that some of them turned out to be a little bit more fair according to our fairness metric, and they have the additional benefit of not being randomized and being more interpretable, right? So in particular, this model 1, model 3 that were produced by the exponential gradient might be preferable to the orange one. Okay. And I think we have 15 minutes left, so I'm going to skip over the exponential gradient exercise, and I'm going to pass baton back to Manojit, who will walk us through the performance through the final kind of comparison of performance of different techniques.
Great. Can everyone see my screen?
Yes.
Yay. Yeah. And so now in this final section, we've trained multiple models on Solver. We first trained a fairness unaware model, and then we trained a post-processing threshold optimizer, as well as a deterministic equivalent. And finally, we trained that exponential gradient in training algorithm. And so now this final section, we sort of want to compare the performance of all the different models we trained across the key metrics. And so first, this is a like small helper function to create some nice visualizations for us. And now we're going to create like a quick dictionary with like the metric frames for each of the models we trained. And now with this helper function, we can now plot the performance of each of our models by the different racial groups. And so here we can see false negative rate broken down by the different racial groups and how each of our models did on them. And so key thing to keep in mind here is that we saw in the original unmitigated model, we had a much higher false negative rate for the unknown racial group compared to the other racial groups. But when we now look at the results of the other fairness mitigated models, we see that we have much lower false negative rate for the unknown racial group. On the other hand, we also see that we keep the false negative rate for the remaining 3 racial groups relatively the same with the 2 approaches, with the both post-processing approaches, the threshold optimizer and the deterministic equivalent seem to get slightly lower false negative rates for all the racial groups. Next, we can plot the balanced accuracy. And so key thing with this is I want to drive home is that we've managed to keep the balanced accuracy relatively the same for all the racial groups across all our models. So even with the unmitigated model and with the post-processing models and the reduction algorithm, we seem to have relatively the same balanced accuracy across all 4 racial groups. So we've managed to keep accuracy the same, but we've also managed to mitigate this fairness-related disparity in our machine learning models using these unfairness mitigation strategies. And finally, for completeness, we can look at the selection rate. And here we can see that the selection rate for the unknown racial group is much lower in the original unmitigated model, and is much higher for the post-processing algorithms across all the racial groups. And once again, the selection rate for the reductions algorithms is relatively the same or better in the reductions algorithm compared to the unmitigated model. Now let's look at the overall model performance. And so now we're just going to look at the overall results for the models. And so we can visualize these results. And the key thing I want to drive here, take home here, is that like the overall performance, so this is a balanced accuracy, not disaggregated by the racial groups, is that the overall balanced accuracy, like as I've been saying, stays relatively the same across all 4 models. We seem to have the same balanced accuracy across all 4 models, but we also have a lower overall false negative rate when we apply these mitigation strategies, and a higher selection rate as well. But if we look at the difference, the maximal differences between the racial groups, and we apply this nice visualization, we see that the disparity in false negative rate is much lower in all our mitigated models. So we have much lower false negative rate disparity in our post-processing algorithms, as well as our reductions approach. In addition, we have a much lower disparity in the selection rate across all our mitigated algorithms compared to the unmitigated model. And we also have a much lower disparity in the balanced accuracy in all our mitigation strategies compared to the unmitigated model. And I want to re-emphasize this because one key thing that has been discussed here was like, hey, how do you decide this trade-off between the accuracy of the model versus choosing a less accurate model that's more fair versus a more accurate model that's unfair? And I think that's sort of a false dichotomy. I think this idea that, hey, in order to achieve fairness, we have to sort of sacrifice accuracy isn't necessarily true. Then here we can see that across multiple models, we've managed to keep the balanced accuracy relatively the same. We've managed to keep the same performance while reducing the fairness-related disparity. So it's possible to sort of like have our cake and eat it too. It's possible to have relatively the same model performance while reducing the model unfairness disparity in the model using these mitigation strategies. And one kind of thing I want to highlight is sort of this idea of these randomized predictions. And so Miro and I have been mentioning this a bit, that both the exponential gradient algorithm and the threshold optimizer yield these randomized predictions. And in certain cases, it may yield a different result given the same input instance. And now, due to these legal concerns or maybe legal regulations or other concerns, you might not be able to deploy the randomized model. And to address these issues, one thing we could do is that we created these deterministic workarounds around this. So for the threshold optimizer, we managed to create a deterministic predictor, a deterministic version of the threshold optimizer that achieved very similar performance to the original threshold optimizer. For the exponential gradient model, we can just actually deploy one of the deterministic inner models rather than the overall exponential gradient model. And another key deployment concern is sort of this idea of access to the sensitive features. So the threshold optimizer requires access to sensitive features during both the training time and the deployment after it's deployed. If you don't have access to the sensitive features once the model's been deployed, you will not be able to use the threshold optimizer. And the exponential gradient model, on the other hand, only requires access to sensitive features during training time. So if you don't have access to your sensitive features after it's deployed and only during training time, it might be worth it to use the exponential gradient model. And so I'll quickly pause here for any questions.
There's currently no questions in the chat, but let's wait a bit to see if there's any new ones coming in.
No questions? Okay, so I'm going to try to wrap this up kind of quickly. And so finally, now we've trained a lot of models. And one thing we want to do is create a model card for our models. So in this paper, Mitchell et al., the authors sort of proposed this model card framework for documenting and reporting the model training details and deployment considerations. And so the model card is a document that sort of highlights the training and evaluation dataset summaries, ethical considerations, as well as quantitative performance results. And I think one small disclaimer is that this Python code works in Google Colab, but it may not work in all the local environments we tested. And so if you're running this notebook locally, this section may not work for you.
Manojit, there's one question in the chat by
Yes.
Nithya. And they ask, just as a reminder, what does access to sensitive features mean?
So access to sensitive features is if you're talking about sensitive features such as race, for example, do you actually have access to that information? And so one example of this would be in credit loans, where when you're sort of trying to determine who gets a credit loan, you actually don't have access to the candidate's race during the model deployment time. Like when the algorithm is sort of determining, should I give this person a loan or not, you actually don't have access to that person's race when they fill out the application. And so you would not be able to use the threshold optimizer in this case because you don't have access to that sensitive feature of race during the model evaluation after it's been deployed. Does that answer the question?
Yes, thank you.
Okay. And so in this final section, so we're going to create the model card toolkit. And so with the model card toolkit, it's sort of like a nice framework for filling out different components of the model cards, specifically such as the model details sections. In this case, we want to include characteristics such as the name of the model, what is it meant to be used for, who trained it, and any sort of other references or licensing issues. In the next section, we want to consider like model card considerations, such as like use cases, like where should it be used, who's meant to use it, and also limitations and ethical concerns. And so with the model card toolkit, you sort of fill out these sections as sort of like dictionaries or lists. And next, when you want to create visualizations, you can sort of pass in visualizations to the model card when you talk about like the training data on the test data. And finally, there's a section called quantitative analysis. And so in this quantitative analysis section, this is where you would put your fairness evaluation results. This is where you would put like, hey, we evaluated these models' results on these disaggregated racial categories, and these are our performance metrics. And so this is a small helper function in order to create some nice visualizations for us. And we fill out all the sections of the model card, and then we can just call the model card toolkit, and it can create a nice HTML model card for us. Okay. And we can view that model card. And so this is an example of the model card looks like for our healthcare assessment model, high-risk patient management model. And so you can see here we have the model details such as the overview, the version, the owners, and the licensing. We have who's the considerations such as who is it used to intended for, the use cases, the limitations that hey, it would not probably generalize outside of hospitals outside the United States because some of the features are inherently tied to the U.S. healthcare systems. And we also talk about some of the risks that we have here. Here we can see a visualization of our training data set. And so you can see the different racial categories for the training data, as well as the target label. And so once again, you see that the target label, readmit 30 days, is balanced within the training data because we applied this rebalancing of the training data. Next, we look at the evaluation or testing data, and we can see the distribution of the sensitive features, race, within the test data set, as well as the distribution of the target label, readmit 30 days within the test data set. And so here you can see the label imbalance that we originally talked about, that overwhelming in the test data set, most of the patients were not readmitted within 30 days. And finally, in the final section, we sort of do the quantitative analysis for the threshold optimizer. And see here we can see the different performance metrics disaggregated by race for the threshold optimizer.
There's a question by Christine.
Yes.
They ask how much of this is illustrating some overfitting of the initial data before including mitigation. Because the fact that your mitigation doesn't really affect the accuracy makes me think the difference in accuracy is kind of noise. Yes, no?
Yes, no. So I definitely say because we didn't apply error bars, so definitely there is some differences in accuracy, but I think if you apply error bars, it would be hard to say that there is not really a statistically significant difference in the different accuracies of the model. But I think it's also hard to say that there isn't a statistically significant difference in the false negative rate parity of the different models. Does that answer the question?
Maybe try it slightly. Let me try it slightly different way. So there are many models that are equally accurate. So very often, like when we're doing machine learning, even like with a small number of features, there can be many different models that are equally accurate. And so creating this secondary criterion acts as a way to zoom in on the one that is not just accurate but also does something else. So Manojit is right that we're not plotting the error bars, but like in our kind of like there was one of these optional exercises when we did that, the difference was actually significant in some of these kind of false positive rates, and in particular models, like they're just kind of going just after accuracy, can be balancing false positive rates and false negative rates differently, right? And still get the same values of accuracy. So it's not so much overfitting. It's more the fact that that going after a single metric gives you kind of like it still leaves the space very open of what the solutions can look like. And we are at the time limit, so maybe I'll let Manojit just kind of show this final section and just do a very quick summary. So basically, we mentioned that it's important to do mitigation at every stage of the pipeline and AI lifecycle, and we gave you examples how to do that. Now there are many questions that you might have afterwards, and each use case is very different. And I want to emphasize that because these use cases are different, like while we're focusing on the set of technical solutions, perhaps in the latter part of the talk, the social aspect is just as important. And in particular, any kind of technical tool needs to be supported by processes and practices, including governmental regulation and government regulation and organizational incentives. So as a couple of ways for you to follow up is either you can join us in the Fairlearn community. So we have weekly community calls. We have quite an active Discord channel, but you can also follow up after this tutorial on the Slack that is ready to do tutorial. So we're really at time. So I would like to thank you all for the attention as well. I would like to thank the team for being available for questions and helping along with the presentation. And again, thanks all for coming and join us either as part of the Fairlearn community or on the Slack afterwards.